Perfect magnetic field. Saturn has the most aligned magnetic field with its rotation axis among all known planets. The tilt between these axes is less than 0.06 degrees, an unusual value within the solar system. This data was obtained after years of measurements by the Cassini probe, which orbited the planet from 2004 to 2017. The expectation was to find some asymmetry, as seen in Jupiter or Earth. However, the observations contradicted all existing models. The generation of magnetic fields in planets occurs through the so-called dynamo process, which depends on the convection of rotating conductive material. A key requirement for this process to work is the presence of asymmetries that stimulate variations in the field. When the field is too symmetrical, like Saturn's, traditional models suggest that the dynamo should shut down. The fact that this does not occur suggests the existence of mechanisms not yet understood. One hypothesis is that Saturn has a layer of liquid metallic helium surrounding its core that smooths out the signals from the field generated deeper down. This intermediate layer could filter out fluctuations and transmit to the exterior only a nearly perfectly aligned field. In this scenario, the internal field could be tilted but invisible to external measurements. This would imply a more complex internal structure than previously imagined. Cassini was essential for refining these measurements. During the final 22 orbits of its mission, the probe passed between the rings and the planet's atmosphere, reducing interference. Only in these close flybys was it possible to precisely detect the magnetic field near the visible surface. The conclusion reinforced the extreme symmetry and led to new theoretical discussions about magnetic dynamics in giant planets. Saturn's rotation could not be determined through radio emissions, as is done with Jupiter, because the field's symmetry eliminated that kind of variation. The solution was to use ring seismology. Internal oscillations of the planet caused detectable patterns in its rings. These patterns revealed that a day on Saturn lasts about 10 hours, 33 minutes, and 38 seconds. This novel approach was crucial for studying Saturn's interior. The absence of drift in Saturn's magnetic poles is also noteworthy. While Earth and other planets show pole migration over time, Saturn appears to keep its poles stable. This reinforces the idea of a field generated under very different conditions. It is still unclear whether this behavior is temporary or has persisted for billions of years. Saturn's magnetic field extends for millions of kilometers and forms a vast magnetosphere. This structure protects the planet against solar wind particles and interacts with rings and moons. It is weaker than Jupiter's but still significant for the system's dynamics. The most intense interactions occur with Enceladus, whose activity directly contributes to the magnetic environment. Enceladus emits plumes of ice and water vapor that inject particles into the magnetosphere. These particles become ionized and generate plasma currents that affect the magnetic field distribution. Cassini detected these interactions indirectly, revealing an active electrical circuit between Moon and planet. This type of electromagnetic connection is rare and reveals the complexity of the Saturnian system. Auroras are also influenced by Saturn's magnetic field. Observed in ultraviolet and infrared, these polar lights are induced not only by the Sun but also by the moons. This feature sets Saturn apart from other planets with more conventional auroras. Charged particles follow the field lines and collide with the atmosphere, releasing luminous energy. The structure of the field suggests a conductive region in depth, probably composed of metallic hydrogen. This material can sustain the dynamo, but how it behaves in Saturn is still poorly understood. Different simulations have been tested to reproduce the aligned field, but none have succeeded completely so far. This indicates significant gaps in our knowledge about the interiors of gas giants. Simulations now attempt to incorporate smooth density transitions between the core and the metallic envelope. These transitions could explain an efficient dynamo even without significant tilt. However, models still fail to maintain field stability over billions of years. Saturn's magnetic behavior remains one of the great challenges of planetary physics. Studies suggest that Saturn's core is diffuse, a gradual mixture of heavy elements with hydrogen and helium. This contrasts with the idea of a solid compact core as previously imagined. The presence of this diluted core would affect how the field is generated and transmitted. New investigations aim to understand this complex interface between internal layers. The magnetic field also affects the particles in the rings. Electrostatic fluctuations and specific orbital alignments may be guided by Saturn's magnetic field. This influences the formation of structures like spokes, dark patches that temporarily appear in the rings. Cassini documented several of these events, correlating them with variations in the magnetosphere. There is also interest in studying the field as an indirect probing tool of the planet. Changes in the field over time may reveal internal mass redistributions. Long-term measurements can indicate slow thermal and convective evolution processes. Thus, the magnetic field becomes a window into Saturn's deep interior. Future missions may send atmospheric probes to pass through the upper layers and directly measure physical properties like conductivity and temperature. This would help constrain planetary dynamo models. Understanding Saturn is essential for studying giant exoplanets. Many of them may show similar behaviors, still invisible with current technology. Seismology on vinyl. Determining Saturn's rotation was a direct challenge resulting from the extreme symmetry of its magnetic field. In Jupiter, variations in the field's radio emissions are used to estimate the planet's day, but in Saturn the field shows no detectable variations. As a result, scientists turned to an alternative method, observing the planet's internal oscillations through its rings. This method is based on the fact that Saturn vibrates like a fluid body in oscillation, generating gravitational disturbances. These perturbations propagate to the rings, where they produce subtle but measurable density patterns. It's the astrophysical equivalent of seismic waves on Earth, but transmitted to a particle disk. This technique came to be known as ring seismology. Cassini was the first mission capable of applying this approach. Saturn's internal oscillations create gravitational resonances with particles in the C ring. These resonances force the particles to organize into regular patterns, such as ripples or bands. By mapping these patterns with optical and radio instruments, scientists were able to infer the exact frequency of the internal oscillations. This frequency directly corresponds to the planet's rotation. The analysis of these data indicated that Saturn's rotation period is 10 hours, 33 minutes, and 38 seconds. This value was published in 2019 after comparison with hydrodynamic models. The accuracy of the measurement depends on correctly identifying the oscillation modes, which are classified by their physical properties. These modes include compressions, shears, and internal gravity waves. Each leaves a distinct signature in the rings. The ability to detect these signatures required extremely high spatial and temporal resolution. Cassini was equipped with the visual and infrared mapping spectrometer and high-definition cameras that monitored the C ring for years. This allowed scientists to build a dynamic map of the ring, revealing previously imperceptible details. It was possible to distinguish even millimetric variations in the spacing of the particles. The measurements revealed not only the rotation rate, but also information about Saturn's internal structure. The oscillation patterns suggest that the planet has an extended core, that is, a gradual density transition rather than a solid boundary. This diluted core mixes with the envelope of metallic hydrogen, which affects the frequencies of the detected waves. Another important discovery was the identification of low-frequency oscillation modes that cannot be explained by models with a compact core. These modes suggest the core extends up to 60% of the planet's radius. This implies a large amount of dense material mixed with gas, something that changes how we understand the formation of giant planets. The data also showed that Saturn's gravitational field subtly varies as these internal oscillations propagate. This provides a new way to estimate the mass and density distribution inside the planet. Thus, ring seismology becomes a tool not only to probe rotation, but Saturn's three-dimensional structure.
The technique has clear advantages over indirect measurements based on magnetic fields or atmospheric winds. It does not suffer interference from external variations and is sensitive to deep layers. However, it requires specific conditions. The rings must be in stable orbit and close enough to be affected by the oscillations. Saturn is, so far, the only planet where this has been successfully applied. The oscillations also reveal details about the planet's internal viscosity and the rigidity of its layers. These properties affect how internal waves propagate, and thus how they appear in the rings. Accurate computational models are needed to correctly interpret the data. The effort is comparable to terrestrial seismology, but adapted to a gassy body. The origin of the oscillations in Saturn is linked to internal convection, rotation, and density gradients. The interaction between these factors generates natural waves that reinforce themselves. At certain points, these waves amplify and become resonant with the orbits of specific ring particles. It is at this point that the observable signature emerges in Cassini's data. The C ring is the primary region used because it has low optical density and little interference from lunar resonances. This makes it easier to identify patterns originating from Saturn rather than those caused by nearby moons. Some regions of the A ring were also studied, but with less success. Choosing the correct region is essential to ensure the validity of the inferences. The ring seismology approach could, in theory, be applied to other planets that may be discovered with dense rings. Exoplanets with similar structures could, in the future, be studied through variations in their disks, detected via transit. This would make Saturn a pioneering model for bodies outside the solar system. For now, the planet is an irreplaceable natural laboratory. The measurements also allowed comparison between internal rotation and atmospheric winds. This revealed that Saturn's upper atmosphere moves more slowly than its interior. The difference between these speeds helps estimate the depth of zonal winds and the composition of the flows. It also contributes to understanding how energy and angular momentum are redistributed within the planet. The technique also showed that the rings are sensitive enough to register seismic events occurring thousands of kilometers deep. This turns the rings into natural sensors of extremely high precision. The results reinforce the idea that these structures are not merely aesthetic, but functional for astrophysics. Cassini proved that the rings can listen to the planet's interior. Enceladus, living E-ring. Enceladus, one of Saturn's moons, is responsible for keeping the planet's E-ring active. Unlike the main rings, which are composed of ancient fragments, the E-ring is continuously replenished with freshly ejected material. This material comes from geysers located at the moon's south pole, which shoot water vapor and ice into space. The particles spread out and form a diffuse and extensive ring. This ongoing activity makes the ring a living and renewable structure. The E-ring extends between 3 and 8 Saturn radii from the planet, with Enceladus orbiting within this range. It is composed mainly of ice grains ranging in size from micrometers to a few millimeters. The density is extremely low but sufficient to be detected by reflected sunlight. Under certain lighting conditions, such as backlight, the ring takes on a pale blue hue. This coloration is caused by the preferential scattering of small particles. The plumes of Enceladus were first detected by the Cassini spacecraft in 2005. The probe flew through these ejections several times, even directly passing through them. On some of these passes, instruments collected samples of particles and analyzed their chemical composition. Measurements confirmed the material was primarily water ice, with small amounts of organic compounds. These plumes are ejected at speeds of up to 400 meters per second. The E-ring shows asymmetries and temporal variations related to Enceladus's activity. When the geysers are more active, the ring's brightness increases. Additionally, particle density around the Moon is higher in the direction of its orbit, where freshly launched particles tend to linger longer. This creates a density gradient within the ring itself. The E-ring, therefore, is sensitive to the Moon's geological variations. The origin of the plumes is linked to 4 major fractures known as tiger stripes. These fissures, about 130 kilometers long, stretch across the Moon's south pole. Through them escape continuous jets of water vapor, ice, and volatile materials. Thermal observations showed these regions are warmer than the rest of the surface. This suggests the presence of an internal heat source, possibly an undersurface ocean. Part of the material ejected by the plumes escapes into space, but a fraction falls back onto Enceladus's surface. This continuous snowfall contributes to the Moon's high reflectivity, with an albedo close to 1. In other words, it reflects almost all incoming sunlight. This phenomenon explains why Enceladus is one of the brightest objects in the solar system. The constant deposition of ice renews the surface, covering impacts and roughness. The geysers are sustained by internal pressures caused by gravitational tides exerted by Saturn. These forces generate cyclic flexing inside the Moon, heating the ice mantle through friction. This keeps water in a liquid state at depth, despite surface temperatures being below -180 degrees Celsius. The pressure and release cycle fuels the fissure's activity. The result is an active system with continuous material exchange. The behavior of the plumes also varies with Enceladus's orbital position. They tend to be more intense when the Moon is at points of greater gravitational stress. This was observed in Cassini's time series data, which detected increases in ejection rates at predictable times. These data helped model the crust's internal behavior and its possible contact with a global ocean. The composition of the E-ring provides clues about the chemistry of the subsurface ocean. Since the particles are launched directly from the interior, their content reveals the original composition. The fact that the ring is composed almost entirely of pure ice indicates low contamination by dust or minerals. This contrasts with older rings, such as the B-ring, which contains material darkened by radiation. The E-ring is constantly renewed. The typical lifetime of E-ring particles ranges from a few hundred to a few thousand years. Radiation and collisions with other particles gradually remove them from the system. Without continuous replenishment by Enceladus, the ring would vanish over short geological timescales. This confirms that the process is currently active, not a remnant of the past. The E-ring is therefore a direct marker of present-day activity. The interaction between Enceladus and Saturn's magnetic field is also relevant. Ionized particles in the plumes interfere with the magnetosphere, altering its local configuration. This was detected by Cassini's plasma instruments and magnetometers. The phenomenon reinforces Enceladus's role as a geologically active body with regional influence. It acts as an emitter of material and energy. The current model assumes that Enceladus's liquid ocean is in direct contact with the rocky core. This favors chemical exchanges between the water and minerals. The fissures then act as natural conduits, releasing pressure and expelling processed material. This makes Enceladus one of the most promising targets in the search for habitable environments beyond Earth. The direct link between interior and space is rare among icy bodies. The E-ring is also used as a basis for optical and spectral calibration experiments. Its nearly uniform composition and low contamination levels make it ideal for sensor comparisons. Scientists use it as a clean background to measure solar interference and instrumental variations. This shows that the E-ring also has technical value in scientific missions. The continuous activity of Enceladus may influence the Moon's long-term orbital evolution. Constant mass loss and particle ejection subtly alter its angular momentum. This effect is still being studied through long-term simulations. It may explain small variations in orbital resonances with other Saturnian moons. The system's dynamics are highly sensitive to this type of disturbance. In addition to its importance to Saturn, Enceladus represents a unique opportunity to study extraterrestrial plumes. Unlike those on Triton or Europa, Enceladus's plumes are accessible and well characterized. This facilitates the planning of future missions, such as probes collecting samples in flight. A landing in an active region is also being considered, focusing on biology and geochemistry.
Ingredients for life in the plumes. The plumes of Enceladus contain more than just ice and water vapor. Analysis of Cassini data revealed the presence of complex organic compounds, silica, salts, and molecular hydrogen. These components are characteristic of hydrothermal environments, similar to those found in thermal vents on Earth's ocean floors. This combination makes Enceladus one of the strongest candidates for potentially habitable conditions beyond Earth. The molecular hydrogen, H2, detected in the plumes is an indicator of chemical reactions between water and rocks rich in iron-bearing minerals. This process, known as serpentinization, releases energy that can sustain microbial life. On Earth, chemosynthetic organisms take advantage of this energy source. The presence of this gas on Enceladus suggests that similar reactions are occurring beneath its ice crust. Amorphous silica was also detected in the ejected grains. This material only forms at temperatures between 90 and 160 degrees Celsius, under high pressure and in the presence of liquid water. This implies the existence of hydrothermal vents at the bottom of Enceladus's ocean. These environments are direct analogs to Earth's deep-sea hydrothermal systems. The combination of heat, water, minerals, and active chemistry makes the location scientifically valuable. Complex organic compounds were identified through Cassini's mass spectrometry analyses. These compounds include carbon chains with oxygen and nitrogen, potentially precursors to amino acids. No forms of life were found, but the necessary chemical building blocks are present. This strengthens the hypothesis that prebiotic conditions could form on Enceladus. The detection of sodium and potassium salts in the ice particles reinforces the idea of a salty ocean. These salts are typical of interactions between liquid water and basaltic rock. The presence of salinity indicates that Enceladus's ocean is not pure, but chemically active. This favors the complexity of internal chemical processes and the possibility of diverse energetic niches. Sound from another atmosphere. The Huygens probe, part of the Cassini-Huygens mission, was the first to land on a body in the outer solar system, Saturn's moon Titan. Launched by the European Space Agency, it detached from Cassini in December 2004 and landed on Titan in January 2005. During its descent, Huygens was equipped with a functional microphone. This microphone was designed to capture sounds during the journey through the Moon's thick atmosphere. It was the first time the sound of entry into an extraterrestrial atmosphere was recorded. The recording revealed the gradual transition between the vacuum of space and Titan's dense atmosphere. The sound began as complete silence, followed by a progressive increase in noise caused by air resistance. As the probe penetrated denser layers, the sounds became more continuous and smooth. Variations in pressure and wind were audible as subtle fluctuations. This transition was studied to characterize the physical properties of Titan's air. Titan's atmosphere is composed primarily of nitrogen, like Earth's, but also contains methane and traces of complex hydrocarbons. The atmospheric density is about 50% greater than that of Earth at sea level. This creates a very efficient medium for sound propagation.
Data from Huygens made it possible to estimate the speed of sound at different altitudes. It also helped infer the air's viscosity and compressibility. The recording was later processed to remove electronic noise and interference. The final result is a continuous soundtrack with subtle variations in intensity and frequency. Engineers used atmospheric acoustics models to correlate the data with specific altitudes. This allowed for an acoustic map of Titan's atmosphere. This process was unprecedented and paved the way for similar experiments on future missions. In addition to atmospheric sounds, Huygens also recorded the noise of its own impact with the surface. Although brief, this sound helped characterize the consistency of the ground. It suggested the surface was composed of granular material, possibly ice particles coated with hydrocarbons. The vibrations also provided data on the soil's rigidity and elasticity. These findings were combined with landing images. During descent, the probe passed through layers of orange haze caused by tholin particles. These particles are formed by photochemical reactions between methane and ultraviolet light. They give Titan's atmosphere its opaque orange hue. The density of this haze varies with altitude and complicates the penetration of sunlight. Even so, the microphone was able to detect pressure changes as the probe passed through these layers. The audio data helped validate Titan's climate models. They confirmed that high-altitude winds are relatively weak, with speeds on the order of a few meters per second. This surprised some researchers who had expected higher speeds based on previous models. The measurements were correlated with temperature and pressure data, completing a detailed vertical atmospheric profile. Huygens also measured its descent speed over time, allowing for highly accurate calculations of atmospheric density. The sound captured by the microphone was synchronized with this data, providing a secondary line of analysis. This redundancy is important for validating instrument methods. The ability to measure atmospheric properties using acoustic sensors may prove useful in future missions to moons with atmospheres. Laboratory acoustic simulations were crucial for interpreting the recorded sounds. Scientists created pressurized chambers with atmospheric compositions similar to Titan's. In these, microphones like the one on Huygens were tested under various conditions. This allowed predictions of how sound would behave during the actual descent. The predictions were confirmed with impressive accuracy. Huygens's sound experience reinforced the importance of non-conventional instruments in space missions. Sounds provide direct information about the dynamics of the environment, complementing visual and spectral data. The use of microphones could be expanded to study storms, volcanism, or even seismic activity. On Titan, this approach was pioneering and highly effective. The sound of the atmosphere also has implications for communication in future crewed missions. Understanding how sound propagates in an alien world helps in designing local communication systems. This will be relevant in future robotic missions with multiple units on Titan. Acoustic properties also affect the operation of rotors, such as those planned for the Dragonfly mission. Huygens's landing was gentle, with a speed below 5 meters per second, aided by the dense atmosphere and multiple parachutes. The microphone recorded this impact as a sudden, brief vibration. After landing, the sounds quickly ceased due to the lack of strong surface winds. This matches a relatively calm and static environment. The stability allowed for data collection for about 70 minutes. The probe continued transmitting data by radio until it lost contact with Cassini, which was out of line of sight. The sound recording was one of Huygens's final transmissions. It provided a valuable resource for the scientific community and a historic record. For the first time, it was possible to hear entry into an alien atmosphere in real time. The mission's success led to the proposal of new acoustic experiments in dense atmospheres, such as those of Venus and Triton. Each environment presents unique challenges in terms of compressibility, temperature, and composition. Titan showed that microphones can function even under extreme conditions. Huygens' legacy continues to influence the design of planetary instruments. The acoustic analysis of Huygens' descent is still used as an example in planetary science courses. Beyond its educational value, it serves as a basis for calibration techniques in future missions. The acoustic characteristics of Titan are now part of the reference dataset of planetary science. Sound has become a new window for studying alien atmospheres. Flying on Titan. Titan presents a unique combination of high atmospheric density and low surface gravity. Surface gravity is only 1.35 meters per second squared, about 14% of Earth's. On the other hand, atmospheric pressure is 1.5 times higher than Earth's at sea level. This relationship makes Titan the only known body where a human, with the right wings, could glide or even fly. This possibility has been demonstrated in several aerospace engineering studies. A human wearing a protective suit and lightweight wings with sufficient surface area could generate lift with little effort. Flapping one's arms or simply running with assisted thrust could be enough to maintain flight. Air resistance and lift would be amplified by the thick atmosphere. This means that flight would be achievable with far less energy than on Earth. Wind tunnel and computational simulations confirm this concept. The high density of Titan's atmosphere not only allows hypothetical human flight, but also favors the use of aerial robotic missions. NASA's Dragonfly mission, scheduled for launch in 2028, is a practical example. The rotorcraft will be equipped with multiple propellers optimized for Titan's air. Its performance is expected to surpass that of similar drones on Earth due to the favorable flight conditions. Dragonfly will be able to travel long distances with relatively low energy consumption. The dense atmosphere provides strong lift, while the low gravity reduces the force needed to maintain altitude. This allows the drone to hop between locations rather than relying solely on ground mobility. It will explore different terrains, including dunes, craters, and possibly even liquid methane lakes. Titan skies will become a gateway to surface exploration. Aside from flight, the dense atmosphere allows for slower falls and higher jumps. An object in freefall reaches a much lower terminal velocity than it would on Earth. This reduces the impact force of landings and minimizes the need for large parachutes. Robotic modules can be deployed with lower risk of damage. These properties make Titan ideal for multi-module or aerial mobility missions. Low gravity directly impacts the effective mass of equipment and payloads. A robot that weighs 100 kilograms on Earth would weigh only about 14 kilograms on Titan. This makes locomotion easier, lowers energy demand, and simplifies instrument transport. Lightweight systems can be used without sacrificing functionality. Operations become more efficient, allowing longer mission durations with limited resources. In addition, Titan's thick atmosphere offers natural protection from cosmic radiation and micrometeoroid impacts. This shielding is rare among celestial bodies and allows for safer long-term surface operations. Electronic instruments are less exposed to high-energy particles. Sensitive components can operate with fewer radiation-hardened designs. Titan is thus more benign than the Moon or Mars in terms of environmental exposure. Flight on Titan would also allow vertical exploration of its layered atmosphere. Scientific payloads could gather data at multiple altitudes, measuring temperature, wind speeds, and chemical composition. This vertical mobility opens a new window into climate dynamics and seasonal changes. Long-range aerial surveys could complement surface landers and provide broader context for observed features. A fleet of aerial scouts could transform Titan exploration. For human missions, Titan offers some theoretical advantages as well. The low gravity and dense air reduce the energy needed for surface movement. Although surface temperatures are extremely cold, the atmospheric pressure is compatible with pressurized suits. Combined with flight capability, this could allow unprecedented mobility. Flying astronauts might one day explore Titan's alien landscapes directly. Environmental conditions also favor the use of lighter-than-air vehicles, such as balloons or airships. These could float for extended periods, offering stable platforms for observation. Long-duration missions could map Titan's surface, monitor weather patterns, and study atmospheric chemistry. Instruments could be suspended at desired altitudes for detailed sampling. The slow winds at higher altitudes would make such vehicles highly stable. Another benefit of Titan's atmosphere is acoustic transmission. Sound travels efficiently through the dense air, enabling communication and navigation via sonar-like systems. Drones and landers could use sound to detect terrain features or avoid obstacles. The acoustic environment could also be used for seismic or subsurface investigations. Titan provides a medium where both airborne and sonic exploration are feasible. Overall, Titan stands out as one of the most promising destinations for future robotic and potentially human exploration. Its environment offers rare opportunities: atmospheric flight, reduced gravity, and natural shielding in one location. Technologies tested here could be adapted for other moons or planets with thick atmospheres. As Dragonfly prepares for launch, Titan continues to capture the imagination of scientists and engineers alike. The skies of this distant moon may soon become our laboratory.
The largest ring is invisible. The Phoebe ring, discovered in 2009 with the Spitzer Infrared Telescope, is the largest and faintest of Saturn's rings. It cannot be seen in visible light, as it consists of extremely diffuse particles. It extends from about 6 to 16 million kilometers from the planet, more than 200 times Saturn's radius. If it were visible, it would span an area larger than 2 full moons seen from Earth. Its scale is colossal, yet its presence remains hidden. The ring is tilted relative to the plane of Saturn's main rings and aligns with the retrograde orbit of the moon Phoebe. Phoebe orbits Saturn in the opposite direction of the planet's rotation, at around 13 million kilometers away. It is believed the ring was formed from debris ejected by impacts on Phoebe's surface. The released particles follow paths that fill the moon's orbital plane, forming a large toroidal cloud. The particles making up the Phoebe ring are extremely small, ranging from micrometers to millimeters in diameter. They reflect very little sunlight, which makes their detection extremely challenging. Infrared sensors, sensitive to heat emitted by sun-warmed particles, were required. Spitzer detected this thermal glow and outlined the ring's shape. Conventional optical telescopes would have been unable to observe it. The ring's vertical thickness reaches up to 40 times Saturn's radius, encompassing an enormous volume. Despite that, its total mass density is extremely low, estimated to be less than that of a small asteroid. Nevertheless, its visual impact would be dramatic if visible from Earth. It would stretch across about 40 full moons in the night sky, creating an immense and eerie spectacle. The ring is responsible for a peculiar phenomenon observed on Iapetus, one of Saturn's mid-sized moons. One hemisphere of Iapetus is darkened by deposits of dark material, while the other remains bright. It is believed that this dark material originates from the Phoebe ring. As particles migrate inward, they collide with Iapetus's surface, creating its distinctive two-toned appearance. This migration of particles is explained by the interaction between sunlight and radiation pressure.
Light exerts a gentle force that pushes particles inward toward Saturn, where some collide with inner moons. The process is slow but constant, and its effects are cumulative over time. On Iapetus, the result is striking and visible at a global scale. It is one of the rare cases where an invisible ring affects a moon's surface directly. Phoebe itself is an irregular and dark moon, with characteristics suggesting an origin outside Saturn's system. It is likely a captured object from the Kuiper belt, or a trans-Neptunian region. Its carbon-rich composition and retrograde orbit support this theory. This would explain why its ring differs in makeup from Saturn's primary rings. It represents a separate class of ring formation. Particles in the Phoebe ring have a limited lifetime within the system. They gradually disperse or are removed through absorption by moons, gravitational scattering, or collisions. Maintaining the ring therefore depends on fresh impacts striking Phoebe's surface. This suggests the ring is being slowly replenished over time. Its existence is dynamic, not static, constantly evolving with the moon's history. Studying this ring provides valuable data on space erosion processes affecting irregular moons. It helps us understand how collisions shape diffuse ring systems in the outer solar system. It also expands our notion of ring geometry. Saturn's rings are not confined to its equatorial plane. The ring system is three-dimensional and intricate, with highly inclined and far-reaching components. Spitzer's infrared observations also allowed scientists to estimate particle temperatures. Under sunlight, they heat to around 100 K, minus 173 degrees Celsius, emitting radiation in the mid-infrared range. This heating provides clues about the surface composition of the grains. Darker particles absorb more light and emit more heat, helping to infer their chemical makeup. These measurements complement spectral analysis techniques. The ring's orbital tilt of roughly 27 degrees renders it invisible to probes and telescopes observing along Saturn's equatorial plane. This explains why it eluded detection by earlier missions such as Voyager. Only out-of-plane observations made its identification possible. The Phoebe ring case highlights the importance of viewing planetary systems from multiple inclinations. Perspective matters in cosmic discovery. The presence of this ring suggests Saturn may host other undiscovered rings. Faint, distant, or non-reflective rings could escape current detection methods. This adds to the complexity of the known ring system. Future observations with more sensitive instruments may uncover new structures. The study of invisible rings has become a growing field in planetary science. The discovery also provides a model for studying exorings, rings around exoplanets. Systems like the Phoebe ring may exist far beyond our solar system. Detecting their infrared glow or transit signatures could be possible with future telescopes. The Phoebe ring serves as a reference for understanding how extensive diffuse rings behave. It's a low-density structure with high orbital impact. Although not directly visible, the Phoebe ring dynamically affects Saturn's outer environment. It contributes to mass redistribution and orbital evolution of distant moons. Its interactions with Saturn's magnetic field are also under investigation, though more subtle. This invisible structure is thus linked to multiple planetary processes. Its ongoing study deepens our understanding of Saturn's architectural complexity. Ultra-thin rings that disappear and create mountains. Saturn's main rings, A, B, and C, may appear thick in images, but their actual depth is surprisingly small. average thickness ranges from just 10 meters to a little over a kilometer, depending on the region. This extreme thinness allows the rings to disappear when viewed edge-on. During Saturn's equinox, sunlight hits the rings from the side. In this alignment, they nearly vanish from sight. These equinox periods offer rare lighting that reveals normally invisible phenomena. One of the most striking are vertical ripples or mountains in the rings. These structures can rise 2 to 3 kilometers high in some areas. They are not solid features, but clusters of particles elevated by the gravity of shepherd moons. Their shadows cast make their height measurable from orbit. These ripples were seen most clearly during the 2009 equinox observed by the Cassini spacecraft. The shadows cast onto the rings indicated hills hundreds of meters to kilometers tall. Scientists used shadow geometry to calculate their exact height. The tallest ones were found in the A ring near the Encke gap. This revealed the gravitational influence of small inner moons like Pan. Pan, a tiny moon about 35 kilometers in diameter, orbits within the Encke gap and exerts gravitational effects on nearby ring particles. Its motion generates both vertical and horizontal waves in the adjacent rings. A similar phenomenon occurs with Daphnis, which orbits within the Keeler gap. Both moons act as shepherds, shaping and disturbing the ring edges. These interactions create well-defined, repeating wave patterns. In addition to moon interactions, resonances with more distant satellites also cause vertical variations. Gravitational resonances occur when a ring particle's orbit aligns with that of a moon. This alignment amplifies tiny forces over time, lifting or depressing groups of particles. These undulating structures can stretch for hundreds of kilometers. Cassini mapped dozens of such ripple formations across the rings. The ring's thinness also allows scientists to study how subtle forces affect vertical material distribution. Tidal forces, electrostatics, and collisions can cause variations from millimeters to kilometers in height. In denser rings like B, these variations are dampened by the greater mass, but in less dense regions like C and D, the structures are more prone to oscillation and vertical displacement. Vertical density in the rings can be inferred from the amount of shadow cast and how the material responds to sunlight. This enables the reconstruction of 3D cross-sections of the ring layers. The data help us understand the collective behavior of orbiting particles. Planetary rings serve as natural laboratories for studying dissipative systems. Cassini's observations provided an unprecedented foundation for this field. During equinox, another phenomenon occurs: the visual collapse of the rings. They become nearly invisible when the sun shines from the side and Earth lies in the same plane. This alignment happens about every 15 Earth years. It was under these conditions that Cassini captured historic images, revealing vertical structures and narrow shadows. These images transformed our understanding of ring thickness. The ring's extreme thinness also raises questions about their long-term orbital stability. Collisions and particle clumping could increase thickness over time, but Saturn's gravity and tidal forces work to flatten them. The balance of these factors determines the final observed geometry. This persistence of this thin profile suggests a young or constantly renewing system. This supports the hypothesis of geologically recent ring formation. Ring thickness also affects their opacity at different viewing angles. Stellar occultation observations allow scientists to measure how much light is blocked at each layer. This reveals how particles are distributed vertically. In some areas, larger particles concentrate near the ring plane. In others, a more homogeneous mix is seen. These findings help model the internal dynamics of the ring system. The ring mountains are not static, they change over time and with the orbits of perturbing moons. This was confirmed by comparing images taken at different times, showing shifts in height and location. These changes indicate that the rings are dynamic and mutable structures, shaped by internal and external forces. High-resolution studies help explain orbital instabilities and energy dissipation. Another key factor is the effect of Saturn's gravity on the stability of these vertical ripples. The planet's strong pull tries to keep particles confined to the equatorial plane. However, localized disturbances can overcome this force temporarily. The result is elevated features that eventually settle back down after a few orbits. This rise and fall cycle provides insights into the system's effective viscosity and elasticity. During equinox, side lighting also highlights spokes, transient dark streaks across the rings. These features form when fine dust particles levitate due to electrostatic repulsion. It's believed that sunlight ionizes the particles, causing them to repel one another and rise above the ring plane. These regions appear dark in optical images and typically vanish within hours. They are most common in the B and C rings. The presence of vertical structures and spokes shows that the rings are affected by multiple simultaneous forces. In addition to gravity, electrical forces, collisions, and micrometeoroid impacts play a role. Each leaves a distinct signature on ring morphology. Careful analysis of these imprints help reconstruct the dynamic history of the rings. Cassini was crucial in capturing the data needed for this process. These observations also provide valuable insights for the study of forming protoplanetary disks. Many processes observed in Saturn's rings are analogous to those in young planetary systems. Vertical ripples, resonances, and dissipative forces also occur at much larger scales around newborn stars. Saturn offers a miniature and more accessible version of these cosmic phenomena. The data collected during the 2009 equinox are still being analyzed by modelers and orbital dynamicists. New computational methods allow for reanalysis of images with greater precision. This has led to retrospective discoveries, including new ripples and previously unnoticed patterns. The dataset is so rich that scientific papers continue to emerge more than a decade later. Saturn's ultra-thin rings have yet to reveal all their secrets.
Ring rain is the name given to the phenomenon in which particles from Saturn's rings slowly migrate toward the planet and fall into its atmosphere. This flow consists of tiny particles of ice, dust, and organic compounds. The particles do not fall like solid bodies, but are guided along Saturn's magnetic field lines. The process creates an ionized drizzle, invisible to the naked eye, but detectable through radio and ultraviolet instruments. The main driver of this migration is the interaction between ring particles and Saturn's magnetospheric plasma. Solar radiation and ion bombardment give the particles electrostatic charges. These charges alter the particles' motion, which begin to follow helical paths toward the planet. This electromagnetic transport is most efficient for smaller particles, especially those under 1 micrometer in size. Observations by the Hubble Space Telescope and Cassini confirmed that this rain primarily occurs at Saturn's equatorial latitudes. It is most intense in areas where the magnetic field lines intersect the rings directly. The rate of infall is not constant, varying with local ring density and magnetic field activity. It is estimated that up to 45 tons of material fall into Saturn every second. This continuous particle influx alters the chemical composition of Saturn's upper atmosphere. Scientists have detected chemical anomalies in specific regions that match the characteristics of incoming material. For example, unusual concentrations of water, oxygen, and organic compounds have been measured in the thermosphere. These elements cannot be fully explained by internal planetary processes, supporting the role of ring rain.
The interaction between the drizzle and the atmosphere generates changes in local electrical conductivity. This affects the propagation of radio waves and creates ionospheric electric currents. Cassini detected variations in Saturn's radio emissions that aligned with regions of ring rain entry. These data helped map the contact points between the ring system and the ionosphere. The atmosphere responds electrically to these deposits. Beyond chemistry and electricity, the ring rain also influences the thermal dynamics of the upper atmosphere. The influx of charged material disrupts the energy balance in the thermosphere. This can lead to localized heating, changes in atmospheric circulation, and the formation of distinct cloud structures. The effect is similar to how Earth's upper atmosphere responds to solar wind, but here, Saturn's rings act as an internal source. Ring rain also contributes to the gradual erosion of the ring system itself. The material lost to Saturn represents a constant depletion of mass. Models suggest that if the current rate continues, the main rings could disappear in less than 300 million years. This supports the theory that Saturn's rings are geologically young. The process of dissipation is natural and ongoing. Particles ejected by impacts on inner moons or by collisions within the rings also feed the rain. These events produce smaller grains that are more easily diverted toward Saturn. The most affected region is the D ring, closest to the planet. Its particles are more likely to be captured by the magnetic field and dragged into the atmosphere. This ring acts as a transitional zone between the disk and the planet. The composition of ring rain particles provide clues about the chemical history of the rings. The presence of complex organic compounds, such as tholins, suggests that the material has been altered by ultraviolet radiation and cosmic bombardment. These processes modify molecular structures and may generate prebiotic molecules. The deposition of these compounds into Saturn's atmosphere is being studied in laboratory simulations. The distribution of the rain is asymmetric between hemispheres and changes with Saturn's seasons. During equinox, when the rings are edge-on to the Sun, solar illumination is minimal. This reduces particle charging and slows electromagnetic transport. During solstice, however, sunlight is stronger and the magnetic field more active, increasing the influx. The rain follows a seasonal cycle tied to orbital geometry. The influence of ring rain has also been observed in localized auroras. Unlike typical auroras caused by solar wind, these are induced by the entry of ring particles. Ultraviolet light detected by Cassini revealed auroral glows synchronized with high influx zones. This demonstrates that the rings play an active role in both the magnetosphere and the upper atmosphere. Their impact extends beyond visual aesthetics. Mass spectrometry experiments helped quantify the elements carried by the rain. Ionized water, molecular oxygen, and hydrocarbons were detected, all consistent with a ring origin. These data were essential in validating models of erosion and atmospheric deposition. For example, the amount of water delivered is enough to affect thermospheric chemistry over short timescales. The exchange is efficient and measurable. This phenomenon of internal rainfall is unique to Saturn among the planets of the solar system. Jupiter, Uranus, and Neptune also have rings, but no similar interaction with their atmospheres has been observed. This may be due to differences in ring structure and composition. Saturn offers a rare combination of ring density, proximity, and magnetic conditions ideal for this process. Its complexity enables such interactions. Advanced plasma dynamics models are being applied to better understand the transport of particles. 3D simulations trace the paths of charged grains under magnetic influence. These studies help predict the most affected regions and their variability over time. The rain leaves electromagnetic signatures that can be detected by future missions. It opens up a new avenue for monitoring ring-atmosphere coupling. Ring rain is therefore a direct link between Saturn's rings and its atmosphere. It exemplifies how an external structure can profoundly shape a gas giant's chemistry and electrical environment. It is a continuous, dynamic, and measurable process. Its implications range from ring evolution to atmospheric science. Cassini revealed that even the faintest components can play a critical role in planetary development.
Colossal hexagon. Saturn's hexagon is one of the most peculiar atmospheric formations in the solar system. It is a stable cloud pattern in the shape of a near-perfect hexagon, located at the planet's north pole. Each side of the hexagon is about 13,800 kilometers long, larger than Earth's diameter. The entire polygon could fit up to 4 terrestrial planets within its boundaries. The structure was first discovered by Voyager in 1981 and confirmed decades later by Cassini. The hexagon is a jet stream that encircles the North Pole at approximately 78 degrees latitude. Unlike most jet streams, which are curved or wavy, this one forms a sharply defined six-sided polygon. The average wind speed within the jet is around 320 kilometers per hour. At the center lies a massive polar vortex resembling a hurricane. This vortex has a defined eye and behaves almost independently of the hexagonal shape. Atmospheric models suggest the hexagon results from interactions between different zonal wind bands with varying speeds. When a jet stream rotates around a pole under certain conditions, it can develop barotropic instability. This instability produces stationary waves that take on polygonal forms. Laboratory experiments with rotating fluids have successfully reproduced similar polygons, including hexagons. The hexagon's stability is remarkable. It has persisted for at least 40 years with no major changes in shape or position. That's unusual for atmospheric structures on gas giants, which tend to be highly variable. The pattern endures despite Saturn's fast rotation and atmospheric shear forces. Its geometric symmetry and long-term persistence continue to challenge meteorological models. The vortex at the center shares characteristics with Earth hurricanes. It features spiraling cloud walls, a central eye, and intense clockwise winds. However, its scale is enormous. The vortex eye alone is over 2,000 kilometers wide. Unlike Earth's hurricanes, this vortex remains stationary over the pole. It also doesn't depend on oceans or a liquid surface to be sustained. Cloud altitudes within the hexagon vary, with upper layers reflecting both visible and infrared light. This has allowed detailed observations by multiple instruments. Cassini used optical cameras, infrared spectrometers, and radar to study the structure. These tools provided data on cloud temperature, composition, and dynamics. The hexagon also affects the distribution of gases like ammonia and phosphine. False color images from Cassini revealed the hexagon in shades of blue, green, and gold, depending on cloud height and composition. True colors, however, change with Saturn's seasons. During northern winter, low sunlight made the pole appear dark and bluish-gray. As summer approached, photochemical compounds built up, shifting the hue to golden tones. These changes reflect seasonal atmospheric chemistry. Seasonal color variation suggests chemical shifts induced by solar radiation. Increased sunlight boosts the production of tholins and other hydrocarbons. These particles accumulate in the upper atmosphere and reflect light differently. This also impacts local opacity and temperature. The hexagon thus serves as a lens for studying Saturn's seasonal evolution and photochemistry. No equivalent hexagon exists at Saturn's south pole. There, a polar vortex is present, but it lacks the six-sided geometry. This asymmetry raises questions about hemispheric balance. It suggests that factors like wind field topology, differential rotation, and thermal gradients are critical. The North Pole appears to host a unique arrangement of conditions conducive to polygon formation. The jet stream that forms the hexagon is estimated to lie 300 to 500 kilometers above the visible cloud tops.
It spans multiple atmospheric layers, indicating a complex vertical structure. 3D computational models attempt to replicate this depth to understand the pattern's stability. Its persistence requires a balance of centrifugal force, Coriolis effects, and pressure gradients. Thermal observations show that the hexagon's interior is warmer than the surrounding atmosphere. Cassini's infrared spectrometry confirmed this temperature difference. The warmth may help stabilize the jet stream, preserving its hexagonal form. The thermal structure may also support the longevity of the central vortex. These findings help refine models of atmospheric circulation on gas giants. The hexagon also interacts with suspended particles in the upper atmosphere, such as haze and aerosols. These particles trace airflow patterns and reveal internal dynamics. Spectral analysis suggests the hexagon influences structures in even higher atmospheric layers. Its impact thus extends well beyond the visible clouds. It acts as an atmospheric organizer at the planetary scale. Cassini observed the hexagon for over a decade, capturing its seasonal changes and temporal consistency. Despite variations in color, thickness, and vortex activity, the hexagonal shape remained intact. Such consistency is rare in planetary meteorology. It underscores the uniqueness of the hexagon in the solar system and the importance of long-term observation. Natural geometric shapes in planetary atmospheres are also studied at other scales. Similar but smaller patterns have been seen in lab vortices and even Earth-ocean currents. However, none match Saturn's hexagon in scale or duration. It remains unmatched as a planetary-scale polygon. As such, it is a subject of ongoing research in geophysical fluid dynamics. Saturn's hexagon sits at the intersection of meteorology, rotational physics, and natural symmetry. Its perfect shape, enduring stability, and immense scale continue to fascinate scientists. It stands as a striking demonstration of fluid physics on planetary dimensions. Since its discovery, it has remained one of the most iconic and mysterious features in extraterrestrial weather.
Dust at 120,000 kilometers per hour. During its journey through Saturn's rings and magnetosphere, the Cassini spacecraft recorded an unexpected phenomenon: the sound of high-speed dust impacts. As Cassini traversed dense regions filled with microscopic particles, it detected individual collisions through its onboard instruments. These grains, often no larger than smoke particles, struck the spacecraft at speeds exceeding 120,000 kilometers per hour. The impacts generated shock waves that were converted into electrical signals. When processed, these signals produced audible pops and crackles. The instrument responsible for detecting these impacts was the Radio and Plasma Wave Science (RPWS) device. Originally designed to study electromagnetic fields and plasma waves, RPWS also proved sensitive to mechanical disturbances. Each dust particle impact created a transient voltage spike in the antenna system. These electrical disturbances were recorded and later transformed into sound files. The result was a real-time audio experience of space dust collisions. The particles detected came from various sources, including Saturn's rings, Enceladus's plumes, and interplanetary space. Their composition varied between icy fragments, silicates, and carbonaceous materials. Many originated from micrometeoroid erosion of the rings, or were ejected by geysers on moons. As Cassini flew through different regions, the frequency and intensity of impacts changed. This variation helped scientists map particle density and origin across the system. The high relative velocity of the impacts, up to 33 kilometers per second, turned tiny grains into high-energy projectiles. Despite their small mass, their kinetic energy was significant. A grain just a few micrometers across could cause measurable disturbances. Over time, the cumulative exposure provided a wealth of data on dust environments.
These measurements contributed to models of ring dynamics and erosion rates. Cassini's sensors distinguished between particle sizes based on the amplitude and duration of the signal. Larger particles created longer, more intense spikes, while smaller grains produced sharp, brief bursts. By analyzing these patterns, researchers estimated the mass distribution of dust populations. This method allowed for passive sensing without visual detection. It was particularly effective in low-light or optically opaque regions. The audio recordings also served as a tool for public outreach and science communication. They allowed audiences to hear what space sounds like through mechanical interaction. Though sound doesn't propagate in a vacuum, the conversion of electrical signals into audio mimics real-world perception. The popping and crackling sequences were both scientific and evocative. They illustrated the dynamism of Saturn's environment in an intuitive way. The densest dust environments were encountered near Enceladus and in the ring plane. The plumes of Enceladus continuously ejected fine particles into space. As Cassini passed through these plumes, it experienced rapid-fire impacts, captured clearly by RPWS. This provided additional confirmation of plume activity. The impacts aligned with visual data from other instruments, creating a multimodal observation. When Cassini dove between the planet and the innermost D-ring during its grand finale, it passed through previously unexplored regions. Engineers expected these regions to be dust-rich and hazardous. Surprisingly, the actual impact rate was lower than predicted. This indicated a cleaner corridor than previously thought. The audio recordings confirmed the low particle density. The detection of interplanetary and interstellar dust was also possible. Some particles had velocities and trajectories inconsistent with Saturn's system. Their origin was traced back to external sources, including comet trails and interstellar grains. Cassini thus became a valuable platform for studying cosmic dust. This data complemented Earth-based measurements and added a planetary-scale perspective. The high-speed collisions also contributed to understanding spacecraft shielding. Each impact, while individually minor, posed a cumulative threat to instrumentation. Engineers used the data to assess wear and degradation. The long-term exposure offered insights into designing future missions through dusty environments, especially relevant for missions to rings, plumes, and cometary tails. Cassini's dust detection added a tactile dimension to planetary science. It demonstrated that spacecraft can feel and hear their surroundings through instrument feedback. This sensing is vital when visual cues are limited. In dense ring shadows or atmospheric hazes, acoustic signatures remain reliable. Such techniques could be applied in future missions with minimal light availability. The RPWS instrument recorded dust impacts alongside plasma and radio emissions. This composite data allowed for correlation between particle flux and magnetic disturbances. For example, dust impacts often coincided with fluctuations in the magnetosphere. This revealed coupling between the physical ring environment and Saturn's magnetic field. Cassini's multi-instrument approach was key to uncovering these interactions. One of the most striking audio recordings came during Cassini's final orbits. As the spacecraft dove repeatedly between Saturn and its rings, it recorded variable impact rates. These rates helped refine models of ring structure and dispersion. In one dive, nearly no impacts were detected, suggesting a broad, empty region. In another, the frequency increased, reflecting micro-ringlets or localized dust clouds. The sounds of dust impacts have since been reprocessed for scientific and artistic use. Some were translated into music for educational purposes, blending science with interpretation. Others were used in data sonification, converting particle patterns into auditory sequences. This method helps identify trends or anomalies that might be missed visually. The Space Dust Symphony remains one of Cassini's most engaging legacies. Cassini's ability to detect and to hear dust at extreme speeds highlights the complexity of ring systems. What appears serene from a distance is in fact a realm of high-speed micro-collisions. Each crackle in the recording marks a moment of interaction between human technology and planetary debris. Together, they form an acoustic map of one of the most dynamic regions in the solar system.
Electric symphony. Saturn is a world of electrical extremes, and Cassini revealed a planet alive with lightning, auroras, and radio emissions. The spacecraft detected storms producing lightning bolts up to 1,000 times more powerful than those on Earth. These superstorms released bursts of radio waves that Cassini could pick up from thousands of kilometers away. The phenomena were concentrated in storm cells in the planet's equatorial and mid-latitude regions. Their signals formed distinct Saturn electrostatic discharges, or SEDs. SEDs were first discovered by the Voyager spacecraft, but studied in depth by Cassini over its 13-year mission. Each SED corresponds to a lightning flash and lasts only a few milliseconds. Yet, due to their intensity, they can outshine all other radio sources in Saturn's magnetosphere. The pattern, duration, and frequency of SEDs offered insights into storm structure and dynamics. Cassini recorded entire seasons of electrical activity on Saturn. The lightning was observed optically and through infrared sensors, confirming its deep origin within thick convective clouds. Storm clouds on Saturn can tower up to 300 kilometers high, filled with ammonia and water vapor. Collisions between ice crystals generate electrical separation, just like on Earth. However, the scale and energy are orders of magnitude greater due to Saturn's atmospheric pressure and composition. In 2010, Cassini observed one of the largest electrical storms ever recorded, known as the Great White Spot. It produced continuous lightning activity for over 200 days. The radio emissions from this storm were so powerful that Cassini's instruments had to adjust sensitivity. The data revealed long-lived storm cells and a network of electrically charged vortices. These events are part of Saturn's seasonal weather cycle. Saturn's auroras add another layer to its electric environment. Unlike Earth's auroras, which are driven mainly by solar wind, Saturn's are also influenced by its rings and moons. Cassini detected auroral ovals that shifted based on the orbital positions of Enceladus and other satellites. The magnetic interaction between the planet and its moons created plasma currents. These currents spiral along magnetic field lines and trigger auroral emissions. These auroras were captured in ultraviolet and infrared, showing dynamic movements around the poles. They pulsated, shifted, and sometimes synchronized with Saturn's rotation. In some cases, they intensified near equinox, when the planet's ring plane aligned with the Sun. The interplay between magnetosphere, solar wind, and internal plasma created a complex, responsive system. The aurora served as a diagnostic tool for Saturn's magnetic field. Saturn's magnetosphere is immense, stretching millions of kilometers into space. Cassini found that it is populated by charged particles from the planet, its rings, and its moons. One of the key contributors is Enceladus, whose geysers inject ionized water into the system. These particles form a torus of plasma that rotates with the planet. Their motion induces currents and electric fields detectable by Cassini's instruments. Cassini's magnetometer and plasma wave instruments recorded waves propagating through Saturn's magnetosphere. These included Alphen waves, ion cyclone waves, and electron plasma oscillations. Many of these waves were modulated by the planet's rotation and ring interactions.
Some were even triggered by impacts from solar storms. The data allowed researchers to reconstruct the structure of Saturn's magnetic field in detail. An unusual feature of Saturn's magnetic field is its near-perfect alignment with the planet's rotation axis. This defies current dynamo theory, which predicts some degree of tilt. Cassini's long-term observations attempted to refine the rotation rate based on magnetic periodicity. The results showed slight variations, suggesting that even Saturn's deep interior participates in the electric orchestra. The field acts as a synchronizing backbone for atmospheric and ring dynamics. A striking discovery was that electric interactions extended to Saturn's rings. Charged dust particles in the rings responded to electromagnetic forces. Cassini observed seasonal spokes, radial markings in the rings, believed to result from electrostatic levitation. These features changed with sunlight exposure and local magnetic field conditions. The behavior of ring particles is deeply intertwined with Saturn's electric environment. Lightning-generated radio waves also propagated into space and were detected at great distances. These signals can reveal storm locations and intensities without visual contact. Radio astronomy thus became a tool for meteorology on Saturn. Cassini's ability to correlate these waves with visible lightning provided ground truth for future missions. It showed that planetary atmospheres can be studied remotely through their electromagnetic signatures. Cassini's instruments also recorded rapid magnetic field reversals and current sheet crossings. These events are caused by distortions in the magnetosphere due to solar wind pressure. Sudden changes in plasma flow rearranged the magnetic topology. This dynamic behavior is similar to Earth's magnetotail reconnection events. Such variability contributes to Saturn's ever-changing electric environment. Electric fields measured by Cassini helped estimate the velocity and energy of charged particles. These data were essential for understanding particle acceleration near the rings and moons. The spacecraft sometimes flew through plasma wakes trailing behind moons. In these regions, electric currents were enhanced, revealing the electromagnetic footprint of each satellite. The system was not only electrically active, it was electrically connected. Even in the outer magnetosphere, Cassini detected electrical signals influenced by internal planetary rotation. The regularity of these signals was used to probe deep processes within Saturn. Fluctuations hinted at interactions between the metallic hydrogen core and the overlying fluid layers. This added an interior dimension to the planet's electric profile. Electromagnetism linked surface, atmosphere, rings, and core. The electric symphony of Saturn illustrates how a planet can become a conductor of cosmic-scale interactions. Lightning, auroras, plasma waves, and ring currents are not isolated phenomena. They are harmonics of a single system shaped by magnetism, rotation, and plasma dynamics. Cassini acted as a floating sensor in this orchestra. Its recordings provided a holistic view of Saturn's electrified complexity.
Spiral diary. Saturn's rings are not uniform. They exhibit highly complex spiral patterns known as density waves. These waves are generated by gravitational resonances with nearby moons, especially Janus and Epimetheus. Each time a ring particle completes an orbit in a specific ratio with a moon, it experiences a slight gravitational tug. These perturbations accumulate, forming tightly packed spiral ridges. The resulting structures propagate like acoustic waves in a solid medium. The spacing between these ridges varies depending on the strength of the resonance and the mass of the influencing moon. The sharpest patterns are induced by Janus and Epimetheus, two co-orbital satellites that swap places every 4 years. This unique orbital dance generates periodic resonances, slightly shifting the position of the ridges with each swap. The rings thus record the moon's presence and motion cyclically, like an orbital diary written in ice. By analyzing the spacing between ridges, scientists can calculate local ring density and infer the strength of each perturbation. The distance between crests decreases as ring density increases. This shows the material behaves as a compressible medium, with perturbations propagating like sound in a fluid. The shape and reach of these waves reveal physical properties such as the ring's viscosity and elasticity. Janus and Epimetheus orbit about 151,000 kilometers from Saturn and share nearly the same path. When they approach each other, the inner moon accelerates and hops to the outer orbit, while the outer one slows and drops inward. This rare phenomenon causes temporary changes in the gravitational field around the rings. The resulting density waves reorganize, subtly altering the spacing and orientation of the crests. Each recorded density wave acts as a time marker, revealing the date of the last significant interaction. Cassini mapped hundreds of these structures in the A and B rings with exceptional resolution. From this data, scientists reconstructed the orbital history of moons that often aren't even directly visible. It's an indirect yet extremely precise form of orbital archaeology. Beyond Janus and Epimetheus, other moons generate similar patterns. Mimas, Enceladus, and Dione induce both density waves and even vertical bending waves. These latter ones affect not just the horizontal distribution of particles, but also their height above the ring plane. Structures created by multiple moons overlap, generating complex interference patterns. Modeling such superpositions requires detailed numerical simulations. The study of these waves also revealed regions where the ring behaves like a non-ideal fluid. In some zones, waves dissipate quickly, indicating high viscosity. In others, waves retain their shape over hundreds of kilometers. These contrasts reflect local variations in composition and particle size. This information helps map the inner structure of the rings with unprecedented accuracy. In some areas, density waves split into branches, indicating multiple resonance sources. This can happen when two moons exert overlapping gravitational influence on the same region. The interaction between these resonances creates secondary patterns like beats and amplitude modulations. Such interference helps scientists understand how orbital disturbances propagate through particle disks, key to modeling protoplanetary disk formation. The height of density waves can also be estimated by shadows cast during equinox. At this time, the sun illuminates the rings edge-on, revealing the vertical relief of the crests. These shadows confirm that the ridges can reach tens of meters high. This reinforces the three-dimensional nature of the disturbances and allows independent measurements of wave characteristics. Density waves are not unique to Saturn's rings. They've also been detected in Uranus's rings and are suspected in Jupiter's. However, Saturn offers the most favorable environment for studying them, thanks to the system's clarity and richness. The wide variety of moons and resonances creates a living library of wave patterns. Each pattern records a specific type of gravitational interaction. The spacing of wave crests serves as an indicator of the disturbing moon's mass. More massive moons generate wider and deeper waves. This relationship has been used to estimate the mass of smaller satellites not easily measured directly. In some cases, wave patterns led to the indirect discovery of moonlets embedded within the rings. That's how the existence of propeller-shaped structures was inferred. The waves also reveal how the rings respond to transient events. For instance, meteoroid impacts can generate temporary radial waves. These disturbances layer atop the regular density waves, creating unique signatures. Temporal analysis of these overlaps helps estimate the frequency and intensity of impacts in the ring system. This is yet another application of ring seismology. Cassini recorded changes in density waves over time, linked to long-term orbital shifts. Gradual moon migration due to tidal forces or secular resonances alters the wave excitation points. This makes it possible to track moon migration over geological timescales. In this sense, the rings function as long-range seismographs, documenting slow celestial movements. These patterns are also sensitive to fluctuations in Saturn's gravitational field.
Changes in the planet's internal structure can slightly shift the orbits of moons and thus the waves they produce. This sensitivity has been used to infer the presence of a diffuse core within Saturn, blended into its mantle. In this way, density waves connect the rings to the planet's deep interior. Altogether, the spiral patterns in Saturn's rings are more than visual curiosities. They are dynamic records of gravitational interactions, orbital evolution, and planetary structure. Each wave contains encoded information about past encounters and present conditions. Thanks to Cassini, this spiral diary can now be read with extraordinary precision, and it continues to offer insights into the physics of rings, disks, and giant planets alike. Propellers in the rings. Within Saturn's A ring, Cassini discovered unusual small-scale disturbances shaped like aircraft propellers. These structures, nicknamed propellers, are caused by the gravitational influence of tiny moonlets embedded within the rings. Though too small to be seen directly, their presence disturbs surrounding particles, creating characteristic twin trails. The resulting shape resembles a miniature airplane with wings of displaced ice particles. These patterns reveal the hidden population of shepherdless moons. The moonlets responsible for propellers are typically hundreds of meters across. Their gravity slightly deflects the orbits of nearby ring particles without carving a full gap. This interaction forms a central void with symmetrical S-shaped wakes on both sides. The size and length of the propeller correlate with the mass of the embedded object. Propellers are typically a few kilometers long, though the central moonlet remains invisible. The largest and most studied propeller was nicknamed Blériot, located in the mid-A ring. Its structure spans nearly 8 kilometers in length and persists over years of observation. Cassini tracked Blériot over multiple flybys, observing changes in its trajectory and structure. These changes hinted at complex interactions between the moonlet, the ring, and nearby density waves. Blériot served as a test case for ring-moonlet dynamics. Propellers are unique in that they occupy a mass range between individual ring particles and full-sized moons. They represent a transitional population, likely remnants of the ring's formation or fragmentation of larger bodies. Their gravitational influence is strong enough to reshape local ring structure, yet it is not sufficient to clear a complete orbit-spanning gap like larger moons do. Their subtle presence reveals the granularity of the ring system. Cassini's images resolved over 150 individual propellers, most of them in the A ring's mid-region. This zone is dense enough to support stable structures, but not so crowded as to erase them quickly. These propellers remain stable for months or even years, depending on ring particle collisions. Their study allowed researchers to probe the mass, composition, and evolution of small-scale objects. They serve as fossils of ring dynamics. The distribution of propellers is not uniform. They tend to cluster in regions where ring density and particle velocity promote long-lived wake structures. These zones are also relatively free of strong resonances from major moons. The absence of disruptive gravitational perturbations allows the propeller trails to persist. By mapping their locations, scientists learned about the local ring environment's stability and turbulence. Modeling the formation of propellers involves N-body simulations of particle-moonlet interactions. These simulations reproduce the twin-lobe disturbances seen in Cassini images. The gravity of the moonlet pulls nearby particles into slightly different orbits, creating trailing gaps. The symmetry of these gaps reflect the uniform rotation and Keplerian shear of the ring. The models closely matched real data from Cassini. Propellers provide insight into the viscosity and cohesion of the ring material. The speed at which gaps refill gives an estimate of how easily particles flow around obstacles. A slower refill suggests stronger particle interactions, or cohesion. A faster refill implies a more fluid-like ring environment. By analyzing propeller evolution, scientists inferred key properties of the ring's internal mechanics. The central moonlets are likely porous, icy aggregates formed by low-speed collisions. Their low density makes them resilient to breakup, but limits their gravitational reach. These bodies may accrete material over time or erode slowly depending on their environment. Their long-term fate is uncertain. They might grow into larger bodies or disintegrate. Cassini's data offer snapshots of these processes in motion. In some cases, propellers exhibit migration across the ring. Their slow radial drift may result from asymmetric particle interactions or density gradients. This drift is important for understanding ring evolution and particle transport. It also shows that even small bodies can change position over time within dense planetary rings. Cassini's long-duration monitoring made such observations possible. Because propellers are three-dimensional structures, they sometimes cast shadows during Saturn's equinox. These shadows confirmed the vertical extent of the disturbances, rising tens of meters above the ring plane. This provided a rare view of the ring's vertical structure. It also validated the scale predicted by numerical models. The combination of light and geometry became a measurement tool. The existence of propellers implies a population of sub-kilometer moonlets hidden throughout Saturn's rings. These objects are likely numerous but hard to detect without disturbances. Cassini's high-resolution imaging and repeated passes were crucial to spotting them. Their study filled a gap in the size distribution of ring particles and moons. It bridges the microscopic and macroscopic regimes. Some propeller-like structures were observed to change over time, possibly due to collisions or variations in local density. These changes included the shape, brightness, and length of the trails. Such variability emphasizes the dynamic nature of Saturn's rings. Even seemingly stable features evolve on short timescales. Cassini's continuous observation allowed scientists to capture this evolution. Propellers challenge the idea of rings as homogeneous disks. They reveal how individual objects can shape their environment through localized gravity. Their interactions illustrate basic principles of orbital mechanics in a real observable system. These lessons apply not only to planetary rings, but to protoplanetary disks and debris fields. Saturn's rings become a natural laboratory for such processes. In sum, the discovery of propellers expanded our understanding of ring-moonlet interactions. These icy microaviators carved patterns that captured the attention of scientists and the public alike. Their trails encode mass, motion, and structure on a small scale. Through Cassini's eyes, we witnessed their delicate choreography across the icy arena of Saturn's rings.
Icy ravioli moons. Saturn's small moons Pan and Atlas have puzzled scientists with their unusual shapes. Both resemble flying saucers or ravioli. These forms are not merely coincidental, but result from the accumulation of ring material around their equators. Pan orbits within the Encke gap of the A ring, while Atlas resides just outside the outer edge of the same ring. Both moons sweep through regions filled with fine particles. Over time, these particles settle along their equators, forming pronounced ridges. Pan is about 35 kilometers across and was first imaged in detail by Cassini during a close flyby. Its equatorial ridge extends several kilometers above the moon's surface, wrapping around its midsection. The result is a smooth, symmetrical bulge that gives it its ravioli-like appearance. The rest of Pan's body remains relatively flattened, enhancing the contrast. This shape was unlike anything previously seen in the solar system. Atlas, slightly smaller than Pan, also exhibits an equatorial ridge but with less symmetry. Its ridge appears smoother and more diffuse, likely due to differences in orbital environment. Both moons have very low gravity, allowing fine particles to adhere loosely without compressing. The shape of these moons is the product of a delicate balance between gravitational attraction and centrifugal force. As particles settle, they form a disk-like collar.
These equatorial ridges are composed primarily of icy particles similar to those in Saturn's rings. Spectral analysis by Cassini confirmed the composition as water ice with low contamination. The process of accretion is gradual. Particles gently collide and stick, forming a loosely bound layer. This layer does not mix with the internal structure of the moons, but remains as a surface feature. It reflects recent geological activity on a small scale. Pan and Atlas are known as ring moons because of their strong dynamical relationship with Saturn's rings. Their gravity clears narrow gaps in the ring system while simultaneously collecting debris. Pan maintains the Encke gap, preventing ring particles from filling it. The balance between clearing and collecting is delicate. It results in both a clean orbital path and accumulation along the moon's equator. The ridges are likely very young compared to the moons themselves. Modeling suggests they formed over tens of thousands to millions of years. This recent activity makes them useful for studying present-day ring-moon interactions. They also provide clues about particle behavior in low-gravity environments. Pan and Atlas act as natural collectors, sweeping up material over long timescales. The shapes of these moons defy traditional expectations of gravitational equilibrium. Most moons tend toward spherical or ellipsoidal forms due to their self-gravity. However, Pan and Atlas are too small to round themselves completely. Their low mass means surface processes dominate over internal deformation. The result is a unique morphology dictated by external accumulation. Cassini's close flybys provided detailed imaging of the moon's surfaces. The equatorial ridges appear smooth and relatively uncratered, suggesting ongoing or recent deposition. In contrast, their polar regions show more irregular terrain and small impact craters. This dichotomy supports the idea of regional resurfacing. The poles are geologically older, while the equators are actively shaped by ring material. The presence of these ridges have implications for satellite formation in dense disk environments. Similar processes might occur in young planetary systems with circumstellar disks. Accretion along a rotating body's equator could influence shape and spin. Pan and Atlas serve as small-scale analogs for larger planetary accretion models. They demonstrate that shape can result from environment, not just internal dynamics. One open question is how stable these ridges are over time. Given their loose structure and low gravity, they may be susceptible to erosion or collapse. Micrometeoroid impacts, tidal forces, or electrostatic charging could disrupt the ridge. Cassini did not observe active reshaping, but the possibility remains. Future missions might observe changes over longer periods. The ridges might also affect the moon's rotational dynamics. The added mass at the equator alters the moment of inertia. This could lead to subtle wobbling or libration as the moons orbit Saturn. Observations of rotational stability might reveal internal density variations. The interplay between shape and rotation offers another avenue of study. Pan's interactions with the ring edge are particularly interesting. It creates edge waves in the Encke gap, subtle ripples shaped by gravitational resonance. These waves confirm Pan's mass and influence, linking it directly to ring structure. The moon not only shapes the gap, but is itself shaped by its environment. The feedback loop between moon and ring is a central theme of Saturn's system. Atlas, although less active in ring sculpting, still exhibits wave patterns in nearby ringlets. Its mass is insufficient to maintain a wide gap like Pan, but it still perturbs nearby particles. These subtle interactions demonstrate that even small bodies can leave measurable imprints. Cassini's high-resolution data made these fine-scale effects visible. The peculiar shapes of Pan and Atlas challenge our understanding of small moon morphology. They show that shape is not always determined by internal processes. External factors, like orbital location and ring density, can dominate in certain regimes. The study of these moons enriches models of body formation, surface evolution, and disk interactions. In sum, Pan and Atlas stand out as natural experiments in particle accretion and orbital mechanics. Their ravioli forms are more than curiosities. They encode the history of ongoing interactions with Saturn's rings. Through Cassini's lens, we learned that even the smallest moons can tell big stories. Their shapes are silent witnesses to the dynamic life of Saturn's complex system.
Surprisingly clean corridor. During Cassini's grand finale in 2017, the spacecraft executed a daring series of dives between Saturn and its innermost D ring. These orbits took it through a region that had never been explored before, the narrow space between the upper atmosphere and the edge of the ring system. Scientists expected this zone to be filled with dust and debris. Instead, Cassini found an unexpectedly clean corridor. The particle density was far lower than predicted. The anticipation of a hazardous environment prompted NASA engineers to prepare for intense shielding. Cassini's high-gain antenna was oriented as a protective shield during its first plunge. Instruments were set to monitor dust impacts and particle density in real time. But to everyone's surprise, the spacecraft encountered almost no significant collisions. The first pass was remarkably smooth and quiet. Data from Cassini's Radio and Plasma Wave Science (RPWS) instrument showed minimal impact noise. Unlike previous traversals through ring material, the RPWS recorded few or no electrical spikes caused by dust grains. This indicated that the region between the D ring and the atmosphere was relatively empty. The silence of this data was one of the mission's most surprising early findings. It contradicted earlier models of ring particle distribution. Prior to the grand finale, scientists had assumed that the D ring would shed a gradual trail of particles inward. This assumption was based on observations of faint structures and scattered light in the innermost rings. Models predicted a dust-laden transitional zone with gradual tapering. But Cassini's measurements showed an abrupt boundary between the ring edge and a cleaner region. The transition was sharper than expected. The lack of debris raised questions about particle transport within the rings. Why were particles not spiraling inward in larger quantities? One possibility is that electromagnetic forces or ring charging repel dust away from the inner boundary. Solar radiation pressure and Saturn's magnetic field may also sweep particles outward. These forces may create a natural cleaning effect near the planet. The discovery allowed Cassini to proceed safely with 21 additional dives through the same gap. Engineers relaxed the shielding protocol after the initial clean pass. This enabled higher-resolution science measurements during later orbits. Instruments like the Ion and Neutral Mass Spectrometer (INMS) and the magnetometer could operate in full. The clean corridor became a unique vantage point for atmospheric and magnetic studies. From this position, Cassini collected detailed data on Saturn's gravity and magnetic fields. The absence of dust allowed uninterrupted observations without contamination. The magnetometer mapped the planet's magnetic field with unprecedented precision. These results contributed to understanding Saturn's internal structure and rotation. The clean environment made these delicate measurements possible. INMS also benefited from the low dust conditions. It sampled Saturn's upper atmosphere and detected molecular hydrogen, water vapor, and hydrocarbons. These constituents offered clues about atmospheric composition and dynamics. The lack of interfering particles improved the fidelity of the mass spectra. As a result, Cassini provided some of the most accurate atmospheric data ever obtained from Saturn.
Cassini's clean corridor discoveries challenged previous ring erosion models. Scientists had believed that micrometeoroid bombardment and ring spreading would populate the inner zone with debris. Instead, Cassini found a region largely devoid of particulate matter. This required revisions to theories of ring decay and material transport. The finding highlighted the need for direct exploration in validating models. The observations also showed that the D-ring itself was thinner and fainter than previously thought. Cassini's close passes revealed subtle wave patterns and brightness variations within the D-ring. These structures may indicate recent disturbances or gravitational resonances, but no evidence pointed to significant inward leakage of particles. The D-ring appeared to end more cleanly than anticipated. The results suggest that Saturn's rings may be more stable and confined than some models propose. If particles are not readily diffusing inward, ring longevity might be greater than expected. This has implications for estimating the age and evolution of the ring system. The rings could be in a more stable equilibrium state than assumed. Cassini's experience echoes findings in other planetary systems. Disks around stars also show gaps and cleared zones possibly shaped by planets or magnetic forces. The clean corridor near Saturn may serve as a small-scale analog. It reinforces the idea that not all gaps are turbulent or dusty. Some may result from sustained dynamic balance. Another implication concerns spacecraft navigation and mission planning. The clean gap was unexpected but offered a natural path for high-risk operations. Future missions to gas giants may seek similar low-risk corridors. The lesson from Cassini is that models must be verified with real measurements. Assumptions can miss critical features of planetary environments. The clean corridor was not just a convenience, it became a key asset of the grand finale. It enabled Cassini to survive longer and gather more precise data than originally planned. The risk turned into an opportunity. This phase of the mission yielded some of the most valuable science of the entire 13-year operation. Ultimately, the surprisingly clean corridor between Saturn and its D-ring exemplified the role of exploration in rewriting expectations. It revealed a hidden simplicity in what was thought to be a chaotic zone. Cassini's passage through this silent gap allowed the spacecraft to peer deeply into Saturn's secrets. And once again, the reality proved more intriguing than the models. Swarm, not solid disk. Despite their serene appearance from afar, Saturn's rings are not solid structures. Instead, they are composed of countless individual particles, ranging in size from micrometers to several meters. These particles orbit Saturn independently in a chaotic, yet gravitationally constrained swarm. The system resembles a densely packed traffic flow more than a rigid surface. There is far more empty space than matter within the rings. Cassini's high-resolution images and instruments revealed that particles constantly collide, bounce, and jostle. These interactions happen at low relative speeds, typically centimeters to meters per second, yet are frequent and dynamic. Each particle orbits Saturn at slightly different velocities based on its radial distance. This differential motion creates shear and turbulence, especially in denser regions. The result is a granular, kinetic environment. The majority of particles are made of water ice with varying degrees of purity. Some are nearly pristine and bright, while others contain dust or organic compounds. The albedo differences across the rings reflect this compositional variety. Cassini's spectrometers confirmed that icy grains dominate, but contamination increases closer to the planet. This affects the color and reflectivity of the different ring zones. Although the rings look like continuous bands, even the densest parts are mostly vacuum. Estimates suggest that the average density is less than a sheet of paper per square meter. This means spacecraft like Cassini could safely pass through gaps with little risk. The illusion of solidity comes from the vast number of particles reflecting sunlight simultaneously. In reality, the system is porous and fluctuating. The A, B, and C rings are visually distinct but share this particulate nature. The B ring is the most massive and opaque, yet even it consists of scattered particles in close proximity. The optical thickness varies dramatically with local clumping and collision rates. Regions of self-gravity wakes, clumps held together loosely by mutual gravity, form and dissolve continuously. These transient features create visible streaks and waves. Cassini's radio and stellar occultations provided cross-sectional profiles of the rings. As starlight or radio waves passed through, the spacecraft measured absorption patterns. These revealed the particle distribution, sizes, and gaps within the rings. The data showed sharp transitions and fine-scale structures invisible to imaging. It confirmed that the rings are layered with complex density variations. The spacing between particles allows sunlight to penetrate and scatter, especially in the C and D rings. This scattering gives rise to ghostly glows and intricate shadowing effects. During equinox, when sunlight strikes edge-on, even tiny features cast long shadows. These visuals helped infer the vertical height and density of ring components. The interplay of light and particles offered a unique observational tool. Gravity plays a crucial role in shaping the swarm. Local gravitational interactions between particles lead to temporary aggregations that can grow into transient clumps or disperse based on collisions and tidal forces. In denser areas, gravitational wakes align into radial streaks, observable by Cassini. These wakes are short-lived but frequent, adding texture to the ring system. The collision dynamics in the rings resemble those of granular flows on Earth. Researchers model them using fluid-like equations adapted for discrete particles. In these models, the viscosity of the ring system arises from collisions, not internal friction. These equations help explain the evolution of ring edges, gaps, and density waves. Saturn's rings act as a natural laboratory for testing theories of particulate motion. The rings also exhibit vertical motion, although the thickness is typically only 10 to 100 meters. Particles oscillate slightly above and below the ring plane. Vertical waves, triggered by inclined moon resonances, modulate this motion further. Cassini's observations of vertical corrugations revealed wave-like distortions extending thousands of kilometers. These structures preserve records of past impacts or disturbances. Despite their chaotic appearance, the rings maintain remarkable radial structure. Resonances with Saturn's moons create sharply defined edges and gaps. Each gap corresponds to a specific orbital resonance, where particle motion becomes synchronized with the moon. These gravitational interactions carve the ring and reinforce order within the chaos. The balance between random motion and resonance keeps the rings stable. Micrometeoroid impacts constantly alter the ring environment. These high-speed grains strike particles, breaking them into smaller fragments or vaporizing surface layers. Over time, this erosion contributes to ring aging and darkening. It also injects new fine particles into the swarm. The rings are not static, they are in a state of continuous recycling and evolution. Electrostatic forces also influence the motion of ring particles, especially the smallest ones. Sunlight can charge icy grains, causing them to levitate or repel each other. These effects are more pronounced during Saturn's equinox. Cassini observed transient spokes, dark radial features caused by charged dust levitating above the ring plane. This is further evidence of a dynamic electromagnetic environment. Cassini's extended mission allowed for repeated passes over the same regions. This long-term monitoring revealed that even stable-looking ring features evolve. Some dense clumps drifted, spread, or dissipated over time. These changes confirmed the fluid nature of the ring system. What seems permanent is in fact ephemeral on decadal timescales. In conclusion, Saturn's rings are not a static disk, but a vibrant, ever-changing swarm. Their apparent solidity masks a complex ballet of icy particles in constant motion. Through Cassini's data, scientists unraveled the intricate physics of this colossal granular system. Understanding these dynamics helps us interpret similar structures elsewhere in the universe, from asteroid belts to protoplanetary disks.
Glowing night. In infrared wavelengths, Saturn reveals a hidden brightness not visible to the human eye. Even on the night side, the hemisphere turned away from the sun, the planet emits a steady glow. This light originates from internal heat rather than reflected sunlight. Cassini's thermal cameras captured these emissions, showing Saturn as lit from within. The planet's night isn't dark, it glows in thermal infrared. Saturn's internal heat comes from two primary sources: residual energy from formation and helium differentiation. As helium condenses and sinks within the hydrogen envelope, it releases gravitational energy. This process, known as helium rain, contributes significantly to the planet's luminosity. Combined with slow contraction, it makes Saturn emit about twice the energy it receives from the Sun. This excess heat sustains atmospheric activity and thermal emissions. Cassini's Composite Infrared Spectrometer, CIRS, mapped these emissions across all latitudes. The instrument revealed temperature variations in the upper atmosphere and highlighted hotspots near the equator and poles. Even on regions experiencing prolonged night during seasonal shifts, infrared maps showed continuous brightness. The data confirmed that Saturn's thermal radiation is planet-wide and relatively stable over time. Infrared allowed Cassini to see the dark side. The thermal glow provided a way to monitor atmospheric circulation on Saturn. Warm belts and cool zones showed distinct patterns associated with jet streams and vortex activity. Long-lived features like the Hexagon at the North Pole emitted a characteristic thermal signature. Cassini's infrared observations helped track the movement of these features through night-side monitoring. This offered insights into heat transport mechanisms within the atmosphere. One of the most striking findings was the detection of thermal asymmetries during seasonal transitions. As Saturn's axis tilts through its 29-year orbit, solar input varies greatly between hemispheres. Yet the planet's internal heat moderates the temperature differences. Cassini observed how night-side regions slowly warmed after winter, even before receiving sunlight. The thermal glow revealed the pace of atmospheric equilibration. Thermal data also showed differences in cloud altitude and composition. Warmer emissions indicated deeper cloud tops, while cooler zones suggested high-altitude hazes. This information was used to infer atmospheric layering and vertical motion. It revealed a complex weather system driven partly by internal energy. Unlike Earth, where sunlight dominates, Saturn's weather is sustained by interior heat. Infrared observations extended to Saturn's rings and moons as well. During eclipses, Cassini monitored how quickly ring particles and satellite surfaces cooled in the absence of sunlight. The main rings cooled rapidly, confirming their low thermal inertia. However, denser parts like the B ring retained heat slightly longer. These differences helped determine particle size and composition in the ring system. The thermal glow also made it possible to image Saturn's night side during occultations. When a background star passed behind the planet, Cassini's instruments used infrared absorption to probe atmospheric structure. This technique revealed temperature profiles with altitude, identifying temperature inversions and layered winds.
It turned Saturn's night side into a powerful tool for atmospheric sounding. During the grand finale dives, Cassini flew through Saturn's upper atmosphere and recorded in situ thermal data. These measurements confirmed the infrared maps obtained remotely. The atmospheric temperature near the equator remained warmer than models had predicted. This helped refine theories on heat retention and radiative balance. The direct and remote data complemented each other for a full picture. Thermal imaging also contributed to understanding Saturn's interior. Differences in emitted radiation pointed to variations in heat flow from within. Areas with slightly higher infrared brightness hinted at possible upwelling from deeper layers. Cassini's thermal observations combined with gravity and magnetic field data helped constrain models of Saturn's core. The internal heat signature is a window into planetary structure. The thermal glow was not constant, but exhibited small fluctuations over time. Some were linked to atmospheric waves and storms, while others related to seasonal shifts. Cassini tracked these variations to study Saturn's meteorological cycles. The planet's night emissions thus became a time-lapse of evolving weather and climate. Thermal light carried information across time and space. Saturn's thermal emission contrasts with the rings, which are colder and emit less infrared radiation. This difference creates dramatic images where the planet glows and the rings appear dark or ghostly. These visuals highlighted the distinct energy sources, internal for the planet, solar for the rings. The infrared contrast sharpened the structural details of both. Instruments on Cassini could switch between visible and infrared views. By comparing day and night images in both spectra, scientists identified features hidden in visible light. Storm systems, heat plumes, and temperature boundaries emerged clearly in infrared. This dual-vision approach expanded the understanding of planetary processes beyond the visible realm. The glowing night of Saturn is not unique. Jupiter also emits internal heat, but Cassini provided the most detailed map of such emissions to date. The mission showed that gas giants remain thermally active worlds. Their appearance in infrared reveals inner workings invisible to sunlight-based observation. This glow is evidence of continued planetary evolution.
Permanent twilight. Even on Saturn's night side, complete darkness is rare. This is due to ring shine, the sunlight reflected by Saturn's vast ring system onto the planet's surface. The effect is similar to moonlight on Earth, but on a much grander scale. The rings act like an enormous diffuse mirror, softly illuminating the planet's night hemisphere. As a result, Saturn experiences a kind of eternal twilight. Cassini captured the ring shine effect in numerous images, especially during the long nights of Saturn's seasonal cycles. The brightness from the rings varies depending on their tilt relative to the Sun and planet. When the rings are fully illuminated, they cast enough light to make shadows and reveal cloud structures. The effect is strongest in the B and A rings, which are denser and more reflective. The C and D rings contribute faintly but consistently. Ring shine adds an ambient glow that persists even when the Sun is completely below the horizon. It provides a soft, scattered illumination over Saturn's night-side atmosphere. Cassini's cameras could detect this glow and use it to observe nighttime meteorology. The twilight effect helped track cloud movement and storm formation without direct sunlight. It became a natural lighting tool for nocturnal imaging. The brightness of ring shine is affected by the albedo and composition of the rings. Denser and cleaner ice particles reflect more sunlight. Regions with contamination or smaller grains produce dimmer reflection. Cassini's spectral instruments use this effect to study ring composition indirectly. Changes in ring shine intensity mapped back to structural and compositional differences. Ring shine is not unique to Saturn.
Jupiter's Galilean moons also experience sunlight reflected from Jupiter's clouds. However, Saturn's ring system makes its version vastly more intense and spatially variable. The sheer surface area of the rings ensures that their reflected light dominates the night sky. This phenomenon is a hallmark of the Saturnian environment. The presence of constant ring shine also has implications for long-term atmospheric chemistry. Continuous low-level illumination can influence photochemical reactions in Saturn's upper atmosphere. Molecules that would typically break down only during the day may continue reacting slowly at night. This subtle effect contributes to the planet's complex atmospheric evolution. For future missions or landers exploring Saturn or its moons, ring shine could provide passive lighting. Even during long nights, instruments could rely on the diffuse glow to operate. Understanding the intensity and variability of this illumination will aid in mission design. Ring shine thus becomes a consideration for future exploration planning. In a broader context, the concept of ring shine enriches our understanding of planetary illumination. It shows how rings are not just passive features, but active participants in planetary systems. Their influence extends beyond gravitational sculpting to include light and energy distribution. They help shape both the appearance and behavior of their parent planet. Saturn's permanent twilight is a poetic consequence of physics, a diffuse glow sustained by billions of icy fragments. Thanks to Cassini, we now understand this glow as a scientific phenomenon with measurable effects. The ring shine turns night into an observable phase, filled with subtle details and quiet energy. It's one more way Saturn's rings shape their world in light as well as matter. Ecological farewell. Cassini's mission ended in 2017 with a deliberate plunge into Saturn's atmosphere, a move guided by planetary protection protocols. This controlled descent was not just a symbolic finale, it was a necessary act to prevent biological contamination. Scientists feared that hardy Earth microbes, possibly surviving on the spacecraft, could one day reach moons like Titan or Enceladus. Both moons harbor environments that might support life. Preserving their natural state was paramount. Enceladus, in particular, posed a concern due to its active plumes ejecting material from a subsurface ocean. Cassini had flown through these plumes and detected water, organics, and signs of hydrothermal activity. This made Enceladus a prime target for future astrobiological missions. Allowing a defunct spacecraft to crash there would risk introducing Earth-based organisms. The same concern applied, though to a lesser extent, to Titan's methane-rich lakes and potential internal ocean. The spacecraft could not be left in orbit indefinitely. Over time, orbital decay or gravitational perturbations might cause an uncontrolled impact with the Moon. To eliminate this possibility, NASA designed the Grand Finale, a series of daring orbits between Saturn and its rings. These culminated in a final trajectory that sent Cassini directly into the gas giant. There, the spacecraft would burn up, ensuring complete sterilization. Cassini's final plunge occurred on September 15, 2017. As it descended into Saturn's atmosphere, it continued transmitting data in real time. Instruments recorded temperature, composition, magnetic field, and atmospheric density down to the last moment. Eventually, increasing pressure and heat destroyed the spacecraft, cutting off communication. This descent transformed Cassini into a probe for its final act. The decision for self-destruction reflected decades of evolving awareness about planetary protection. The Committee on Space Research, COSPAR, mandates that missions avoid contaminating worlds that may harbor life. These rules became more stringent as evidence of habitable environments on moons like Enceladus grew. Cassini's fate was a direct result of this ethical and scientific responsibility. The concept of forward contamination, sending microbes from Earth to other worlds, is a real concern. Certain bacteria can survive extreme cold, vacuum, radiation, and time. Although Cassini was assembled in clean rooms and underwent sterilization, total decontamination is impossible. A crash into an ocean world could allow microbes to persist and multiply, jeopardizing future life detection missions. By plunging into Saturn, Cassini avoided creating long-term biological ambiguity. Any future discoveries of life in the Saturnian system would be more trustworthy, untainted by previous missions. The ecological farewell preserved scientific integrity. It also underscored humanity's growing recognition of its impact beyond Earth. Space exploration carries ethical obligations as well as scientific goals. The ecological sacrifice had engineering implications. Cassini had to retain enough fuel to navigate its final orbits and enter the desired trajectory. Mission planners timed the final burn precisely to align the spacecraft with Saturn's atmosphere. Even the angle of entry was carefully calculated to maximize data return and ensure destruction. Nothing was left to chance. The spacecraft's final data packets were received by the Deep Space Network on Earth. These included real-time measurements from the ion and neutral mass spectrometer and magnetometer. The signal grew weaker as Cassini fell deeper until it was lost forever. This moment marked the end of a 13-year journey at Saturn and a 20-year mission since launch. The emotional impact of Cassini's end resonated with scientists and the public alike. Many had worked on the mission for decades, witnessing its discoveries reshape our understanding of the outer solar system. The ecological farewell gave closure and a sense of purpose. It was not a failure, but a final contribution, scientifically rich and ethically sound. Cassini's end also set a precedent for future planetary missions. Missions to Europa, Ganymede, or Enceladus will need similarly careful end-of-life planning. Planetary protection has become a cornerstone of mission architecture. It reflects a shift from exploration at any cost to responsible stewardship of the solar system. Cassini led by example. The ecological farewell was an extension of Cassini's scientific philosophy. Throughout its mission, the spacecraft was guided by precision, care, and curiosity. Its end was no different, meticulously planned, rigorously justified, and deeply meaningful. It turned destruction into discovery and risk into respect. The finale aligned science with conscience. In preserving Saturn's moons, Cassini also preserved our ability to search for life credibly. The legacy of its ecological farewell will live on in future missions. As we prepare to send landers, drills, or submersibles to icy worlds, we must ensure that what we find is truly alien. Cassini's sacrifice made that possible. Saturn's atmosphere now holds the ashes of a machine that once explored its rings, moons, and mysteries. Cassini became part of the planet it studied, leaving no debris, no contamination, only data. It burned brightly in its last seconds, a fitting tribute to a mission defined by excellence. The ecological farewell was both an ending and a safeguard for the future. Eyed hurricane beyond Earth. At Saturn's south pole, Cassini discovered a massive hurricane with a clearly defined eye, a rare feature outside Earth. The structure included an eye wall, spiral cloud bands, and a central vortex, all hallmarks of a terrestrial tropical cyclone. Yet unlike Earth's hurricanes, this storm is locked in place over the pole and not driven by ocean heat. It is one of the few known planetary storms with a distinct eye. Its scale and persistence are extraordinary. The eye measures about 2,000 kilometers across, nearly 20 times larger than a typical hurricane eye on Earth. Surrounding it is a ring of towering clouds, forming the eye wall, where winds spiral inward at high speeds. Cassini's infrared imaging showed these cloud tops rising more than 30 kilometers above surrounding areas. The sharp boundary and symmetry suggest sustained and organized atmospheric dynamics. The visual similarity to Earth hurricanes was immediately striking. Winds within the storm reach speeds of approximately 500 kilometers per hour. These wind speeds exceed those found in the strongest Earth hurricanes. Cassini's cameras captured multiple layers of motion, including internal rotation within the eye. Despite this, there is no ocean or latent heat cycle fueling the storm. Instead, it appears to be powered by internal heat and deep atmospheric convection. The energy source remains an active area of study. The hurricane was first observed by Cassini in 2006, shortly after arriving at Saturn. It remained nearly stationary at the South Pole throughout the mission. Unlike mid-latitude storms that migrate across a planet, this polar vortex is anchored by planetary rotation and pole-centric forces. It may be stabilized by a combination of Coriolis effect and vertical convection. This makes it a long-lived atmospheric structure. Infrared instruments revealed warm temperatures in the storm's core compared to surrounding regions. The temperature gradient supports strong vertical motion and suggests a warm core cyclone. This is unusual among gas giants, where most vortices are cold-cored. The heat likely originates from Saturn's interior, rising through deep atmospheric layers. This warmth sustains the convection and circulation over extended timescales. The storm is not isolated, but part of a broader polar weather system. Cassini observed additional vortices and turbulent flows nearby. These smaller features interact with the main hurricane, sometimes merging or spiraling around it. This resembles vortex dynamics seen in laboratory simulations of rotating fluids. Saturn's polar pole behaves like a natural fluid dynamics experiment on a planetary scale. Optical images show the storm surrounded by concentric cloud bands. These bands rotate at different speeds and interact with each other through wave patterns. Cassini tracked changes in the cloud structures over several years, noting seasonal variation. As Saturn approached equinox, lighting conditions revealed more about vertical cloud structure. This allowed scientists to measure cloud height and density. The presence of such an organized system raises questions about similar phenomena on other gas giants. Jupiter has massive vortexes like the Great Red Spot, but lacks a symmetrical eyed hurricane. Saturn's unique thermal and rotational conditions may foster these polar cyclones. The high angular momentum at the poles could support such formations indefinitely. It's an ongoing mystery in comparative planetary meteorology. Cassini's data showed that the storm's base lies deep within the troposphere, possibly reaching into the stratosphere. The vertical extent is much greater than Earth hurricanes, which are confined to the troposphere. This vertical reach affects chemical mixing, cloud formation, and heat transfer. Studying it improves our models of atmospheric layers on gas giants, and it also offers insight into their internal energy distribution. The storm does not generate lightning, a feature often associated with strong Earth storms. Cassini's radio instruments found no significant lightning discharges in the eye or surrounding bands. This suggests differences in atmospheric composition and charge dynamics. The absence of lightning helps distinguish it from convective storms in Saturn's mid-latitudes. It is a quieter but more massive phenomenon. Despite its scale, the polar hurricane shows remarkable stability. Over the 13 years of Cassini observations, it maintained its location, size, and structure. Only minor variations in cloud texture and brightness occurred. This persistence implies a delicate balance of atmospheric forces. It highlights Saturn's ability to sustain large-scale structures for decades or longer. Saturn's polar regions differ dramatically from its equatorial zones. The pole lacks the alternating jet streams seen at mid-latitudes. This may allow the storm to develop without interference from zonal wind bands. The absence of lateral shear could support the formation of a coherent, long-lived vortex. Saturn's unique atmospheric profile makes this possible. The hurricane contributes to overall pole warming as warm air from deeper layers is cycled upward. This could influence chemical reactions and haze formation in the upper atmosphere. Cassini spectrometers detected differences in gas composition within the eye. These findings help trace the vertical movement of materials within Saturn's weather system. The presence of this hurricane at the South Pole complements the hexagonal jet stream at the North Pole. Each pole hosts a massive and unique atmospheric structure. Studying both provides a comparative view of polar meteorology. Cassini gave us the first detailed look at these features, changing our understanding of gas giant dynamics. In summary, Saturn's south polar hurricane stands as one of the most remarkable weather systems in the solar system. With its defined eye, extreme winds, and long lifespan, it defies easy classification. It challenges our understanding of atmospheric circulation in planets without surfaces or oceans. Thanks to Cassini, this planetary hurricane now serves as a benchmark for comparative atmospheric science.
Extreme winds. Saturn is home to some of the fastest winds in the solar system. Jet streams in its upper atmosphere reach speeds of up to 1,800 kilometers per hour. These winds are primarily found near the equator and run in east-west bands, similar to Earth's jet streams but on a much larger scale. The velocities far exceed those observed on any other planet, including Jupiter. Cassini provided detailed measurements of these atmospheric flows. The strongest winds occur at the equatorial belt, where cloud bands move rapidly in a prograde direction. These equatorial jets were observed to be symmetric across the equator, a rare feature among gas giants. Cassini tracked the motion of cloud features over time, enabling precise velocity calculations. The wind speeds were sustained over long periods, showing remarkable stability. This made Saturn's equator a key site for atmospheric studies. The high-speed winds are believed to result from a combination of solar heating, internal heat, and planetary rotation. Saturn emits more energy than it receives from the Sun, driving convection deep within the atmosphere. As warm gases rise and cool, they contribute to horizontal wind shear. The planet's rapid rotation, one day lasts about 10.7 hours, amplifies the Coriolis effect. This leads to the formation of strong, stable jet streams. Unlike Earth, Saturn's atmosphere lacks a solid surface to disrupt flow patterns. This allows jet streams to develop with fewer constraints, reaching higher velocities. The smooth transition between atmospheric layers reduces friction, enabling persistent high-speed winds. Saturn's low density and thick gaseous envelope further enhance vertical and horizontal wind transfer. These factors collectively support extreme wind regimes. Cassini's infrared observations confirmed the vertical extent of some jet streams. Winds were found not just at cloud tops, but extending hundreds of kilometers deeper. This vertical coherence indicates a coupling between different atmospheric layers. Some models suggest that Saturn's winds may originate from convective activity below the visible clouds. Heat from the interior could help maintain these deep jets. Wind speeds vary significantly with latitude. Besides the powerful equatorial jet, Saturn hosts alternating bands of eastward and westward winds at higher latitudes. These bands are narrower and slower but still reach several hundred kilometers per hour.
The pattern resembles the zonal banding seen on Jupiter but is less turbulent. The bands define Saturn's striped appearance when viewed in visible light. One unique feature of Saturn's winds is their temporal consistency. Unlike Jupiter's more chaotic weather systems, Saturn's bands remained relatively unchanged throughout the Cassini mission. Some seasonal variations occurred, especially near solstices and equinoxes, but the core jet streams showed minimal fluctuation. This indicates a dynamically stable, long-term wind structure. Cassini's data allowed scientists to model atmospheric dynamics more precisely. The mission provided wind profiles at different altitudes, latitudes, and times. These were used to refine general circulation models of gas giants. The extreme wind speeds helped validate predictions from fluid dynamics and thermal balance theories. Saturn became a test bed for atmospheric physics. In some regions, the fast-moving air creates shear zones where clouds stretch and twist. These shear regions can give rise to storms or turbulence. Cassini observed waves and eddies forming in such areas, especially near the boundaries of jet streams. These features provide insights into energy transfer and dissipation. The high-speed winds are not just steady currents, they shape the weather. The effects of these winds extend beyond atmospheric motion. They influence temperature gradients, cloud composition, and even magnetic field interactions. For instance, jet streams can modulate how heat escapes from Saturn's interior. The alignment of cloud particles along jet paths also affects albedo and reflectivity. Thus, Saturn's winds play a role in both climate and visual appearance. Wind measurements relied on multiple Cassini instruments, including imaging systems and the visible and infrared mapping spectrometer. By tracking cloud motion across different wavelengths, scientists estimated speeds and directions. These measurements were cross-validated with thermal imaging and Doppler shifts. This multi-instrument approach ensured high data reliability. Cassini also compared Saturn's wind patterns to other planets. Compared to Earth, Saturn's wind energy is vastly higher due to size and speed. Even Jupiter's famous jet streams are slightly slower than Saturn's equatorial currents. This comparative analysis revealed fundamental differences in gas giant meteorology. Each planet has unique wind dynamics shaped by its internal and orbital properties. Despite the extreme speeds, Saturn's atmosphere appears deceptively calm in visible light. The cloud layers are relatively smooth, with few large-scale storms visible. This makes the high-velocity winds even more surprising. Underneath the serene appearance lies a powerful and complex atmospheric engine. Cassini helped unveil this hidden dynamism. Seasonal changes on Saturn may modulate the jet stream slightly. As solar energy shifts between hemispheres over Saturn's 29-year orbit, wind intensity and location can drift. Cassini observed subtle changes in wind speed correlating with the approach to equinox. These long-term patterns provide clues to atmospheric inertia and adaptability. Great white spots. Saturn experiences colossal storms known as great white spots approximately once every Saturnian year, about every 29 Earth years. These storms are massive convective events that erupt in the planet's atmosphere, becoming visible across vast latitudinal bands. They appear as bright white disturbances spanning thousands of kilometers, hence the name. Each event is powerful enough to encircle the entire planet within weeks. Only a handful have been recorded since the early 20th century. The most recent Great White Spot was observed by Cassini in 2010. It began as a small bright area in Saturn's northern hemisphere and rapidly expanded. Within days, the storm stretched over 15,000 kilometers in length. It generated shock waves and temperature anomalies in the upper atmosphere. Cassini's instruments captured the storm's evolution in unprecedented detail. These storms originate from deep within Saturn's troposphere. Internal heat builds up beneath a stable atmospheric layer until it breaks through, releasing massive amounts of energy. This leads to the rapid formation of towering convective clouds. Water vapor condenses and rises, forming a bright white top visible in visible light. The energy release is similar to Earth's thunderstorms, but on a planetary scale. The great white spots influence atmospheric dynamics across Saturn. As the storms expand, they generate planetary-scale waves and disrupt jet streams. These waves can persist for months, altering wind patterns and cloud structures globally. Some storms even create long-lived vortices as remnants. The interaction with Saturn's banded cloud system provides insight into atmospheric coupling. Cassini's radio and infrared instruments detected significant changes in atmospheric temperature during the storm. Hotspots developed where the storm injected heat into the upper layers. These temperature anomalies lasted long after the visual storm subsided. This revealed how deeply such storms influence Saturn's atmospheric energy balance. They act as major climatic events. Spectral analysis showed chemical changes in the storm-affected regions. Cassini identified alterations in ammonia, phosphine, and hydrocarbon distributions. These chemicals were likely dredged up from deeper layers by the storm's vertical motion. The process gave scientists a rare view of Saturn's lower atmosphere. Great white spots serve as natural probes into normally hidden regions. The storms also produce intense lightning, detected by Cassini's radio and plasma wave science instrument. These discharges are among the most powerful in the solar system. They confirm strong vertical convection and the presence of water-based clouds deep within the atmosphere. The lightning also helps trace storm development and structure over time. Each great white spot is unique in size, duration, and impact. Historical records from telescopes show variability between events. Some storms last months, while others persist for over a year. The frequency and characteristics may be linked to Saturn's seasonal cycle. As the planet tilts in its orbit, solar heating patterns shift and may trigger instability. In visible light, the storms are strikingly bright against Saturn's generally muted atmosphere. They outshine surrounding clouds and become prominent features in planetary images. The high albedo results from thick ammonia ice clouds at the storm's summit. These clouds reflect sunlight efficiently, making the storms easy to detect even with ground-based telescopes. After the storm subsides, it leaves behind a turbulent wake. This can include dark belts, cloudless regions, or filamentary structures. These remnants gradually fade but can persist for years. Cassini observed how post-storm regions evolved, revealing patterns of atmospheric recovery. It showed Saturn's atmosphere slowly re-establishing equilibrium. The mechanisms triggering these rare outbursts are still under investigation. Some models suggest slow accumulation of moist air beneath a stable layer. When buoyancy finally overcomes the barrier, a runaway convective burst ensues. This threshold-based model explains the long intervals between events. However, other factors like rotation and magnetic fields may also play a role. Great white spots have also been observed to influence Saturn's stratosphere. Cassini detected warming in the upper atmosphere directly above the storm. This stratospheric hotspot indicates vertical wave propagation and energy transfer. Such effects demonstrate that storms can impact the planet's atmosphere from bottom to top. They are vertically integrated phenomena. The 2010 storm provided a wealth of data thanks to Cassini's continuous monitoring. Researchers studied the storm across multiple wavelengths, comparing it with previous events. This allowed for the most comprehensive analysis yet of a great white spot. The data continue to inform models of storm genesis and planetary-scale atmospheric dynamics. Future missions to Saturn could benefit from real-time monitoring of the next great white spot. Long-term orbital presence would be ideal to capture pre-storm conditions. Observing the buildup, trigger, and aftermath in detail would advance understanding of gas giant meteorology. The next event may occur around 2039, depending on the cycle. Moon-planet electric cable. Enceladus, one of Saturn's icy moons, forms a remarkable electromagnetic connection with the planet. As it orbits within Saturn's magnetosphere, the moon's plumes of water vapor and ice grains interact with magnetic field lines. These plumes originate from fissures near the moon's south pole and contain charged particles. When they are ejected into space, they ionize and create a plasma environment. This forms a direct link, like a natural electric cable, between Enceladus and Saturn. Cassini detected these interactions through its magnetometer and plasma instruments. As the spacecraft passed through the region, it observed disturbances in Saturn's magnetic field. These perturbations aligned with the moon's location and activity level. It became clear that the plumes weren't just passive features, they were actively influencing the magnetic environment. The interaction created currents along magnetic field lines. This coupling is known as a plasma circuit, similar to the well-known Io-Jupiter interaction. Enceladus acts as a generator, injecting material into Saturn's magnetosphere and altering its structure. The plasma torus created by this activity surrounds Saturn and contributes to its auroras. Unlike Io, which ejects sulfur and oxygen, Enceladus contributes water group ions. This gives Saturn's inner magnetosphere a unique chemical profile. The plumes themselves bend the magnetic field lines as they pass through them. This deflection, or magnetic field draping, was observed directly by Cassini. The field lines curve around the plume, confirming the presence of conductive material and ionized gases. The interaction zone is centered on Enceladus's orbit and varies with the intensity of the geysers. This creates a dynamic and ever-changing electromagnetic region. Electrons accelerated along magnetic field lines generate radio and ultraviolet emissions. These emissions were picked up by Cassini's radio and plasma wave science instrument. They confirmed the existence of field-aligned currents flowing between Saturn and Enceladus. These currents carry energy and information between the two bodies. The result is a constantly shifting plasma connection. This plasma circuit contributes to Saturn's auroral activity. At specific magnetic latitudes, auroral spots appear that correspond to Enceladus's orbital position. These bright patches were observed in ultraviolet by the Hubble Space Telescope and confirmed by Cassini. The connection between the Moon and planet is not just magnetic, it's also luminous. The electric cable glows with activity. Enceladus's influence extends beyond localized magnetic perturbations. The plasma it injects can alter the overall density and dynamics of Saturn's inner magnetosphere. This affects how charged particles move, how energy is transferred, and how the system responds to solar wind. The Moon acts as both a source and a sink of plasma. It shapes the electromagnetic landscape. This discovery changed the way scientists think about moon-planet systems. Small moons like Enceladus can have outsized effects due to active geophysical processes. The idea that a moon can plug in to a planet's magnetic field adds complexity to planetary science. It introduces a new kind of interaction beyond gravity and tidal forces. Electromagnetic coupling became a key theme of the Cassini mission. Cassini's multiple flybys of Enceladus were carefully planned to investigate these effects. Instruments recorded changes in ion density, magnetic field strength, and wave propagation. The data allowed scientists to model the structure of the plasma environment. These models showed how Enceladus's motion through Saturn's field induced electric currents. It demonstrated a full electromagnetic circuit. The intensity of the coupling varies with the plume activity. When Enceladus's geysers are stronger, the plasma injection rate increases. This enhances the electric currents and strengthens the auroral response on Saturn. Conversely, during periods of lower activity, the coupling weakens. This variability makes the system responsive to Enceladus's internal dynamics. The source of the charged particles is the ocean beneath Enceladus's icy crust. As water escapes through the south polar fissures, it carries salts and organic molecules. When exposed to space, this material becomes ionized by solar radiation and magnetospheric interactions. Thus, the Moon's internal ocean is indirectly linked to Saturn's magnetosphere. It's a deep connection, both physically and electromagnetically. One consequence of the plasma circuit is a drag force on Enceladus's orbit. The interaction transfers angular momentum from the Moon to Saturn's magnetic field. Over long timescales, this could alter the Moon's orbital parameters. It represents a feedback loop between orbital motion and electromagnetic dynamics. Cassini's data are being used to quantify this effect. The plasma connection also affects radiation levels near Enceladus. By injecting particles into Saturn's magnetosphere, the Moon modifies local radiation belts. This has implications for spacecraft safety and instrument calibration. Cassini adjusted its operations to account for these variations. Future missions will benefit from this knowledge when planning Enceladus flybys. Magnetic reconnection events may also occur near the Moon. These are sudden releases of stored magnetic energy, similar to solar flares. Cassini observed brief, intense changes in field direction and particle energy consistent with such events. This adds a dynamic layer to the interaction, with transient bursts of energy. The Moon-planet connection is not only steady, but also capable of sudden change. In summary, Enceladus forms a literal electric link to Saturn via its plumes and plasma. This natural circuit influences magnetic fields, auroras, radiation belts, and even orbital mechanics. Thanks to Cassini, we now understand how a tiny icy moon can electrically shape a gas giant's environment. It's a powerful example of interconnected planetary systems.
Orbit swap, Janus and Epimetheus. Saturn's moons Janus and Epimetheus share one of the most unusual orbital configurations in the solar system. They co-orbit the planet in nearly identical paths, just 50 kilometers apart. But instead of colliding, they engage in a gravitational dance, exchanging orbits every 4 Earth years. This phenomenon is known as a co-orbital swap. It's a natural orbital resonance with no exact parallel among major moons. Janus orbits slightly closer to Saturn than Epimetheus for several years. Since it moves faster due to its lower altitude, it gradually catches up to Epimetheus. When they approach, gravitational interactions cause a momentum exchange. Janus moves outward, taking Epimetheus's former orbit, while Epimetheus shifts inward. After the swap, the cycle begins anew, a continuous ballet of orbital motion. Cassini tracked these exchanges in detail, providing high-resolution imagery and orbital data. The swap is smooth and non-collisional because of the Moon's relative sizes and timing. Janus is roughly twice the mass of Epimetheus, which helps stabilize the dynamic. The gravitational tug is subtle, yet sufficient to redirect their paths. This celestial choreography is governed by Newtonian mechanics. The orbital swap preserves energy and momentum within the system. No external force drives the exchange. It arises purely from mutual gravitational influence. The timing is precise, with each approach leading to a switch that avoids close collision. Over decades, this pattern repeats with remarkable consistency. The orbital elements oscillate within narrow bounds. The interaction is a rare case of a horseshoe orbit in celestial mechanics. If plotted in a rotating reference frame, each moon traces a horseshoe-shaped path relative to the other. They move closer, diverge, and switch places without ever overtaking in a straight pass. This dynamic is common among asteroids sharing orbits with planets, but almost unheard of for moons. Because of their co-orbital motion, the moons are sometimes described as co-satellites. They are not bound to each other gravitationally like a binary pair, but are linked through the shared orbit. Each moon remains gravitationally bound to Saturn, but their mutual influence defines their behavior. Their interaction is a long-term orbital resonance. Cassini's instruments detected slight changes in orbital speed and altitude during each swap. The timing of these variations allowed precise modeling of the mass and structure of both moons. The mission confirmed the theoretical predictions with empirical measurements. It provided one of the clearest real-world examples of co-orbital motion in the solar system. The moons are relatively small. Janus measures about 179 kilometers in diameter, and Epimetheus about 113 kilometers. Their irregular shapes and low densities indicate they are likely porous and loosely compacted. This suggests a history of gentle accretion rather than violent collision. Their continued coexistence supports this gentle origin scenario. Surface features on both moons show signs of cratering and past impacts. These geological records offer insights into the history of Saturn's inner moon system. Differences in crater distribution may reflect slight variations in exposure to ring debris. The orbital swap itself does not cause surface changes, but it influences their positions within the debris environment. The swap has implications for ring-moon interactions. Janus and Epimetheus lie just outside Saturn's main ring system. Their orbits place them near the edge of the A-ring, influencing ring particles through resonances. These interactions can cause subtle features such as wave patterns or density variations. The moons act as dynamic sculptors of Saturn's rings. The orbital dance also provides a natural laboratory for celestial mechanics. Janus and Epimetheus illustrate how gravity governs complex systems over long timescales. Their predictable interaction helps validate numerical models of orbit evolution. It offers a benchmark for studying other potential co-orbital systems, including exoplanets. The configuration likely formed early in the Saturnine system's history. Over time, tidal forces and orbital migration brought the moons into this resonant relationship. Their low relative velocity at close approach prevents destructive encounters. Instead, gravity balances the system into long-term stability. It's a product of natural dynamical tuning. Cassini's extended mission allowed it to observe multiple orbital exchanges firsthand. Each event matched predictions, reinforcing confidence in the models. The dataset remains a valuable resource for researchers studying orbital dynamics. The moon's behavior is now one of the best documented examples of natural co-orbital motion in the solar system. Janus and Epimetheus are not alone in sharing an orbit, but their size and proximity make them exceptional. Most co-orbitals, like Trojan asteroids, are separated by much larger distances. These moons, however, are close enough for direct imaging and measurement. Their interaction is visible and quantifiable, not just theoretical. In conclusion, the orbital swap between Janus and Epimetheus is a striking example of gravitational choreography. Every few years, they trade places in a perfectly timed exchange that has persisted for millennia. Thanks to Cassini, this dynamic system is now a textbook case of co-orbital motion, elegant, stable, and uniquely Saturnicanning.
Breathing fractures, Enceladus's tiger stripes. Enceladus's south pole features 4 prominent linear depressions known as tiger stripes. These parallel fractures are approximately 130 kilometers long and spaced evenly apart. They are named Alexandria, Cairo, Baghdad, and Damascus Sulci. Unlike typical surface cracks, these fissures are active. They emit plumes of water vapor, ice particles, and organic compounds. Cassini provided the first close-up observations confirming their role in ongoing geological activity. The tiger stripes are thermal anomalies.
They are significantly warmer than surrounding terrain. Cassini's composite infrared spectrometer, CIRS, revealed temperatures near 200 Kelvin, much higher than expected for Enceladus's icy surface. This elevated heat is concentrated along the central axes of the fractures. The warmth enables subsurface liquid water to reach the surface through narrow vents. These vents act as breathing points for the Moon. Jets of material escape from these fractures in periodic bursts. Cassini observed more than 100 distinct geysers during its close flybys. The plumes consist primarily of water vapor, with traces of ammonia, methane, carbon dioxide, and complex organics. The material is ejected at speeds up to 2,000 kilometers per hour, enough to escape Enceladus's gravity and contribute to Saturn's E-ring. The process is continuous, though modulated by tidal forces. Tidal stress from Saturn drives the opening and closing of the tiger stripes. As Enceladus orbits the planet in an elliptical path, gravitational forces stretch and compress the Moon. This flexing causes the fractures to widen and narrow over time, influencing plume intensity. Maximum emissions occur when fractures are most open near orbital apocenter. Cassini confirmed this correlation through repeated measurements. The source of the plumes is a global subsurface ocean beneath the Moon's icy shell. Cracks in the ice allow this ocean to communicate with the surface. Models suggest the water rises through narrow channels or porous ice, picking up salts and organics on the way. The ocean lies beneath a 20 to 30 kilometer thick ice crust with a depth of up to 10 kilometers. The tiger stripes serve as direct conduits to this hidden sea. Enceladus's geysers are not explosive, they are sustained and stable. Observations show that the plumes have persisted for at least decades and likely much longer. The regularity and consistency of the emissions suggest a long-lived geological engine. Internal heating, likely from tidal dissipation, maintains the ocean in a liquid state. This makes Enceladus one of the most promising habitats for life. The fractures themselves have distinctive ridged morphology. Their edges show evidence of icy buildup from repeated venting. This material accumulates as frost and cryovolcanic deposits. Over time, it reshapes the surface near the stripes, creating textured terrain. Cassini's high-resolution images reveal fine-scale features, including fissures, pits, and fractures within the stripes. These details help map activity zones. The chemistry of the plumes supports the possibility of hydrothermal reactions at the ocean floor. Cassini detected silica nanoparticles and molecular hydrogen in the ejecta, signatures of warm, rocky interaction. This implies the presence of hydrothermal vents similar to those found on Earth's ocean floor. Such environments are considered potential cradles of life. The tiger stripes are thus linked to deep astrobiological significance. Enceladus's surface near the tiger stripes is geologically young. Crater counts show a lack of impacts, indicating recent resurfacing. The area is dominated by ridges, grooves, and flows. These features suggest tectonic and cryovolcanic activity continue to reshape the region. The fractures are the most prominent signs of this ongoing internal dynamism. Their activity contrasts with the Moon's otherwise inert appearance. Cassini flew directly through the plumes multiple times, sampling their composition. The Ion and Neutral Mass Spectrometer, INMS, detected a rich blend of gases, including organic molecules with more than 4 carbon atoms. These are precursors to biologically relevant compounds. The plumes act as natural exhaust from Enceladus's internal ocean. This allows remote sensing of subsurface conditions without drilling. The presence of continuous outgassing implies pressure regulation within the ocean. The tiger stripes serve as relief valves, balancing internal pressures caused by heat and tidal flexing. Without these vents, pressure could build and cause catastrophic ice fracturing. The steady emissions show that Enceladus has evolved a self-regulating mechanism. This makes the Moon's geology both dynamic and sustainable.
Seasonal variations influence the plume activity subtly. As Saturn moves through its orbit, sunlight changes the thermal environment of Enceladus. However, tidal forces remain the primary driver of stripe activity. Cassini monitored long-term variations to distinguish between thermal and gravitational influences. This temporal data is key to understanding how the fractures breathe over time. The fractures also shape the distribution of surface ice. Material falls back as fine snow, accumulating across the southern hemisphere. This snowfall brightens the terrain and helps maintain Enceladus's high reflectivity. The southern pole is the brightest region of the Moon. This recycling of plume material links internal processes with surface appearance. The fractures themselves might not be static. Some models suggest they slowly migrate or evolve over time. Crustal movements, ice shell thinning, or shifting tidal stress could modify their configuration. Cassini's repeated imaging offers a time series for detecting such changes. The persistence and variability of the tiger stripes make them windows into Enceladus's geologic evolution. In summary, Enceladus's tiger stripes are more than surface features. They are active gateways to a subsurface ocean. Through these fractures, the Moon vents water, organics, and heat into space. They regulate pressure, sustain the E-ring, and reveal conditions favorable to life. Thanks to Cassini, these breathing fractures are now key targets for future exploration.
Organic sands of Titan. Titan, Saturn's largest moon, hosts vast equatorial dune fields composed not of silicates, but of organic particles. These dunes span hundreds of kilometers in length and reach heights of up to 100 meters. Unlike Earth's deserts, Titan's sand is made of solid hydrocarbons, molecules like benzene and acetylene. They are the result of atmospheric photochemistry driven by solar ultraviolet light and Saturn's magnetospheric energy. This makes Titan's dunes a surface expression of atmospheric chemistry. The dunes are primarily located between 30 degrees north and south latitude. They are confined to low-lying areas where wind and topography allow sediment accumulation. Radar images from Cassini revealed long, linear ridges aligned predominantly west-east. These ridges are spaced several kilometers apart and stretch over dark plains. The consistency and global distribution suggest active sediment transport. Cassini's synthetic aperture radar, or SAR, was crucial for mapping the dune fields. Titan's thick haze blocks visible light, but radar penetrates the atmosphere and reflects off the surface. These returns showed dune patterns analogous to those found in Namibia and Saudi Arabia. The similarity is striking, though the composition and wind dynamics differ. This allowed scientists to draw parallels with terrestrial aeolian processes. The formation of the organic grains involves complex atmospheric chemistry. Methane and nitrogen in Titan's upper atmosphere undergo photolysis, producing a cascade of organic compounds. These descend as aerosols, accumulating and possibly coagulating into larger particles. Over time, these materials reach the surface, forming a reservoir of dune-building sediment. The source is entirely endogenous to Titan. Wind is the main agent shaping the dunes, but its behavior on Titan is unusual. The dense atmosphere, about 1.5 times Earth's pressure, means particles require less force to move. However, surface winds are generally weak, with episodic gusts from seasonal changes or methane storms. These occasional strong winds are sufficient to transport the light hydrocarbon grains. The result is a slow but persistent dune migration. The dunes are mainly found in regions with low radar reflectivity, suggesting smooth and homogeneous surfaces. Their dark appearance contrasts with brighter icy highlands and possible cryovolcanic areas. The contrast helps distinguish dune-covered terrain from other geological features.
Dune regions cover approximately 13% of Titan's surface, an area larger than the Sahara. Spectral analysis from Cassini's Visual and Infrared Mapping Spectrometer, or VIMS, supports the hydrocarbon composition. Peaks in infrared reflectance align with known organic functional groups. Although exact grain composition remains uncertain, candidates include tholins, complex organic substances formed from nitrogen and methane. These findings indicate Titan as an organic-rich world, geologically and chemically. The dunes align with Titan's global circulation patterns. Winds driven by Saturn's seasonal changes create a longitudinal flow near the equator. These winds shape the dunes over thousands of years. Some deviations in orientation suggest local influences from terrain or transient wind systems. This interplay between global and local factors mirrors Earth's own aeolian systems. Titan's gravity is about 1/7 that of Earth, and this influences sediment dynamics. The low gravity allows particles to saltate more easily, even with minimal wind. Combined with the thick atmosphere, this makes Titan's surface highly conducive to dune formation. These conditions enable dunes to persist over long timescales, with little erosion or removal. The dunes reveal clues about Titan's climate history. Their orientation, spacing, and morphology encode past wind regimes. By modeling these patterns, scientists can infer how Titan's atmospheric circulation evolved. Some theories propose that past climatic shifts may have altered dune fields, leaving behind inactive or reoriented structures. Titan's surface holds a record of atmospheric processes. Despite their prominence, Titan's dunes are confined to specific elevations and latitudes. They avoid polar regions where methane lakes dominate the surface. This geographic segregation suggests a strong climatic influence on sediment availability and mobility. Equatorial dryness favors dune stability, while polar humidity leads to sediment cohesion and lacustrine deposition. Cassini's radar observations identified interdune areas that appear rougher and possibly contain icy bedrock. These exposed zones might act as barriers or sediment sources. The interaction between dunes and underlying terrain shapes regional dune field evolution. Understanding these dynamics helps interpret how Titan's surface and climate interact over geological timescales. Some dune fields are bordered by bright, elevated terrain. This may represent older crustal material resistant to erosion. The juxtaposition of organic dunes and ancient icy uplands highlights Titan's diverse geologic history. It also shows how sediment transport is shaped by both wind and topography. The overall landscape is a product of integrated surface processes. Future missions, such as the Dragonfly rotorcraft, aim to study these dunes directly. Dragonfly will explore the equatorial regions and analyze organic sands for composition and structure. This mission will provide ground truth for Cassini's remote sensing data. It may also reveal insights into prebiotic chemistry on Titan. The dunes are thus both geological and astrobiological targets. In conclusion, Titan's equatorial dunes are vast reservoirs of complex organics shaped by wind, chemistry, and climate. They represent a unique aeolian system unlike anything on Earth. Thanks to Cassini, we understand their origin, structure, and environmental context. These organic sands offer a window into Titan's dynamic surface and the possibilities of chemistry beyond Earth.
Methane rivers on Titan. Titan, Saturn's largest moon, is the only body besides Earth with stable liquids on its surface. But here, the liquid is methane. Titan's surface temperature, around 94 Kelvin, allows methane and ethane to exist as liquids. These hydrocarbons form lakes, seas, and rivers that define a complete hydrological cycle.
Cassini's radar and near-infrared instruments confirmed widespread fluvial networks. The rivers shape valleys, deltas, and even canyons. Methane on Titan behaves much like water on Earth. It evaporates under solar heating, condenses into clouds, and precipitates as rain. These rains carve channels across the landscape, feeding into larger basins. This continuous recycling of methane forms Titan's equivalent of a water cycle. Seasonal shifts in solar exposure drive variations in rainfall and river activity. Cassini's radar imaged thousands of branching channels, some hundreds of kilometers long. Many resemble terrestrial river systems in structure and complexity. Dendritic patterns suggest long-term erosion by flowing liquids. These networks are especially common in polar regions, where methane lakes are abundant. Some rivers drain directly into seas like Kraken Mare or Ligeia Mare. Flow direction and channel morphology provide clues about regional slopes and tectonic structures. Cassini revealed river valleys aligned with tectonic faults, suggesting structural control. The rivers cut through varied terrain, from icy plains to hilly highlands. In some cases, the channels incised deep into the crust, forming canyons over a kilometer deep. This indicates persistent or high-energy flow over geologic timescales. Spectral data confirmed the channels are carved by liquid methane, not lava or dry processes. Titan's atmosphere contains about 5% methane, replenished continuously from surface reservoirs. Without this cycle, atmospheric methane would be destroyed by sunlight in about 10 million years. The rivers help maintain atmospheric balance by recycling methane. This process links surface activity with atmospheric chemistry. Some river systems appear dry, showing no active flow during Cassini's visits. These may represent ephemeral or seasonal streams, active only during Titan's summer. Others show evidence of repeated flooding, with layered sediment deposits at mouths. Cassini observed transient darkening of regions after suspected rainfall events. These observations support active, albeit infrequent, hydrological dynamics. Titan's low gravity and thick atmosphere modify river behavior. Liquids flow more slowly, and channels can remain stable with minimal gradient. Wind resistance is high, reducing wave formation and erosion by wind. This allows rivers to maintain narrow, deep paths without wide floodplains. The result is a landscape with intricate, preserved fluvial features. Some rivers feed into expansive seas near the poles. Kraken Mare, the largest, spans over 1,000 kilometers and receives input from multiple river systems. The interface between rivers and seas forms deltas and submerged channels. These features indicate sediment transport and deposition at basin margins. Cassini's radar altimetry confirmed varying depths and submerged inflow points. Hydrological modeling of these systems suggests a complex balance between precipitation, evaporation, and subsurface infiltration. Titan's surface likely contains porous ice or organic sediments that absorb some methane. However, impermeable icy bedrock limits percolation, directing flow across the surface. The balance of runoff versus infiltration shapes river longevity and morphology. Cassini's discoveries challenge the assumption that active fluvial systems require warm, wet conditions. Titan's rivers show that surface liquids and weathering can occur in a cryogenic environment. They broaden the definition of planetary habitability and geological activity. The existence of methane rivers proves Titan has a dynamic surface despite its extreme cold. Comparative studies reveal that Titan's fluvial networks are as complex as Earth's, scaled for gravity and fluid properties. Flow patterns mimic terrestrial analogs in both structure and evolution. This makes Titan an ideal case for studying universal principles of erosion and drainage. It also provides a rare example of active geology on an icy moon. The formation of methane rivers depends heavily on atmospheric replenishment. Titan's climate cycles may regulate river formation over tens of thousands of years. Orbital parameters and solar flux influence long-term weather trends. These variations could shift river locations and activity zones. Cassini provided a temporal snapshot within this broader context. Future missions may observe changes in river activity with seasonal progression. Monitoring changes in channel reflectivity, rainfall frequency, and lake levels will provide dynamic insights. The Dragonfly mission plans to land in equatorial dunes, but may later investigate fluvial regions. Rivers remain crucial targets for understanding Titan's environmental processes. Methane rivers also influence Titan's potential for prebiotic chemistry. The transport of organics and interaction with varied surface materials creates chemical diversity. Some riverbeds may accumulate tholins and nitrogen compounds from atmospheric fallout. These materials, once deposited and processed, could mimic early Earth environments. Titan thus becomes a natural laboratory for chemical evolution. In summary, Titan's methane rivers are a testament to active geological and atmospheric interplay in a cryogenic world. They form a robust hydrocarbon cycle that shapes the Moon's surface and sustains its atmosphere. Cassini revealed their extent, dynamics, and importance, rewriting what we know about extraterrestrial rivers. These flowing features remain one of Titan's most Earth-like and enigmatic traits.
Icy Pebbles, Huygens landing site. On January 14, 2005, the Huygens probe descended through Titan's thick atmosphere and landed in a riverbed-like terrain. Images taken just before touchdown revealed a surface strewn with rounded ice blocks resembling river pebbles on Earth. These features were later interpreted as icy seisos, pebbles sculpted by flowing liquid methane. Their shape and distribution suggested transport and erosion by past fluvial activity. It marked the first direct contact with Titan's surface. The landing occurred in the Shangri-La region, near bright highlands and dark plains. The area had been previously imaged by Cassini's radar, but Huygens provided ground truth. Upon descent, the probe captured over 700 images and a suite of atmospheric and surface data. The final landing site was characterized by flat terrain with scattered rounded objects. These objects measured a few centimeters across and cast short shadows. Spectroscopic analysis confirmed the surface materials were primarily water ice. However, the pebbles had a coating of complex organics, consistent with Titan's atmospheric chemistry. The dark deposits covering the ice were likely tholins, organic compounds formed by ultraviolet photolysis of methane and nitrogen. These compounds settle from the atmosphere and accumulate over time. The result is an Earth-like landscape with alien materials. The shapes of the pebbles were consistent with fluvial rounding. Their smoothness and lack of angularity pointed to mechanical abrasion by fluid transport. On Earth, similar morphology forms in riverbeds where rocks tumble and collide in moving water. On Titan, methane flows serve this role, carrying ice particles and sculpting them into rounded forms. Huygens offered the first visual evidence of such erosion beyond Earth. The pebbles were embedded in a dark matrix, possibly composed of finer grains or damp sediment. Some objects appeared partially buried, indicating past flow or settling. The overall texture suggested a stable surface, not a recent floodplain. However, the landscape could be periodically reactivated by methane rain. The presence of pebbles implies at least intermittent surface flow in Titan's recent past. Huygens' Descent Imager Spectral Radiometer, DISR, documented the final approach to the surface. The images revealed a branching network of dark channels converging near the landing site. These channels had the morphology of fluvial drainage basins, with tributaries feeding into main valleys. This network strengthened the case for past liquid flow. The pebbles were likely remnants of that process.
Meteorological data collected during descent showed a dry lower atmosphere with potential for surface evaporation. While no surface methane was directly observed, humidity and wind profiles supported a past climate capable of rainfall and runoff. The probe's instruments recorded no splash or bounce on landing, suggesting a firm, dry surface. The icy pebbles lay atop a frozen but stable ground. Temperature readings at the surface indicated a cold environment of around 94 Kelvin. At this temperature, water is rock solid, but methane and ethane can be liquid. This makes fluvial activity feasible in Titan's climate. Over long timescales, repeated cycles of methane rain and runoff could transport and round ice fragments. The landscape captured by Huygens records these environmental rhythms. The presence of such pebbles adds to the evidence of an active methane hydrological cycle. Titan's surface is shaped not only by atmospheric deposition, but by fluid erosion. The pebbles suggest sediment transport processes that mirror Earth's river dynamics. Yet the materials involved, ice and methane, create a cryogenic twist. This makes Titan a unique analog for comparative planetary geology. Post-landing analysis of images and sensor data helped reconstruct surface composition and mechanical properties. The pebbles appeared to rest stably, with no visible movement during Huygens' descent. The surface reflected orange light from the hazy atmosphere and had low albedo. These observations were consistent with the presence of tholin-coated ice. The landscape was both familiar and alien. The rounded ice fragments imply a long history of erosion, likely spanning millions of years. Titan's slow hydrological processes mean changes occur over extended timescales. Unlike Earth, where rivers flow frequently, Titan's rivers may be episodic but geologically significant. Each pebble is a time capsule of ancient flows. They testify to Titan's dynamic surface environment. Cassini later imaged similar regions across Titan, identifying channels and alluvial fans. These features supported the interpretation of Huygens' site as fluvially shaped. The global prevalence of such features indicates that Titan surface processes are not isolated. River-like erosion is a widespread phenomenon. The Huygens site is a representative piece of a larger system. While Huygens remained stationary, it transmitted valuable data for over 72 minutes after landing. This data included temperature, pressure, and spectral measurements. It gave scientists a detailed snapshot of surface conditions. Combined with imagery, the mission provided unparalleled insight into Titan's fluvial landscape. The icy pebbles became a cornerstone of that understanding. The Huygens mission demonstrated the value of in situ exploration. Orbital imaging can suggest surface features, but only landers can confirm material properties. The identification of icy pebbles validated remote sensing interpretations and offered new questions. How often do Titan's rivers flow? What are the long-term climatic cycles? The surface holds the answers. In summary, the icy pebbles found by Huygens are direct evidence of methane-driven erosion on Titan. Their shape, composition, and context confirm past fluid transport in a cryogenic world. They link Titan's atmosphere, surface, and climate in a tangible way. Thanks to Huygens, we now see Titan not just as a haze-covered moon, but as a world with rivers, erosion, and icy stones shaped by alien rain.
Hot internal clock, Saturn's excess heat. Saturn emits nearly twice as much energy as it receives from the Sun. This discrepancy indicates the presence of an internal heat source independent of solar input. Infrared measurements from Earth-based telescopes and spacecraft like Voyager and Cassini confirm this thermal excess. The planet radiates strongly in the infrared spectrum, especially at night. This internal energy output reveals deep processes within Saturn's interior. The leading explanation for Saturn's excess heat involves helium rain. Inside the planet, hydrogen and helium exist in a metallic high-pressure state. As Saturn cools, helium becomes immiscible in metallic hydrogen and begins to separate. The helium droplets fall toward the core, releasing gravitational energy as heat.
This ongoing process contributes significantly to Saturn's thermal emission. Cassini data supported this model by measuring the composition and distribution of Saturn's atmosphere. Observations showed a depletion of helium in the upper atmosphere compared to solar proportions. This matches predictions from helium rain models, where helium sinks and concentrates deeper. The heat from this separation maintains convection in Saturn's outer layers. It delays the planet's overall cooling over billions of years. Another contributor is residual heat from Saturn's formation. As the planet formed, gravitational collapse converted potential energy into thermal energy. Some of that heat remains trapped in the deep interior. Over time, this energy is released slowly through conduction and convection. Saturn's size and composition help retain heat longer than smaller terrestrial planets. The internal pressure inside Saturn exceeds several million atmospheres near the core. Under such conditions, hydrogen transitions into a metallic state, behaving like a liquid metal. This metallic hydrogen conducts electricity and heat efficiently, facilitating energy transport. The dynamics of this region influence both magnetic field generation and heat flow. It creates a complex thermal and electromagnetic environment. Saturn's temperature structure is not uniform. The upper atmosphere is colder than expected, while the deep interior remains hot. This temperature gradient drives convection, the upward movement of warm material. Convective motions help transport internal heat to the upper layers. These dynamics are key to understanding atmospheric behavior, including storms and jet streams. Cassini's infrared instruments mapped Saturn's thermal emission in fine detail. Observations revealed that the planet glows faintly in the infrared, even on its night side. This glow is due to internal heat, not reflected sunlight. The night side radiation provides a clean signal of Saturn's intrinsic energy output. It also helps distinguish seasonal versus permanent thermal features. The planet's gravity field, as measured by Cassini's flybys, helps constrain interior models. Small variations in gravity across latitudes reflect differences in mass distribution. These data are used to refine estimates of core size and composition. They suggest a diffuse extended core mixed with lighter elements. This structure affects how heat is stored and transported. Saturn's excess heat influences its weather and atmospheric circulation. It fuels convection cells that drive banded cloud patterns and massive storms. For example, the Great White Spots, periodic planet-encircling storms, are powered in part by internal heat. Without this energy, Saturn's atmosphere would be more static. The heat sustains atmospheric activity even far from the Sun. The combination of helium rain and slow cooling provides a long-term heat source. Unlike Jupiter, whose heat budget is better explained by residual formation energy alone, Saturn requires additional mechanisms. The planet's lower mass and cooler core necessitates helium phase separation. This distinction highlights the diversity among gas giants. It shapes how scientists model planetary evolution. Understanding Saturn's heat flow informs theories about exoplanets. Many gas giants outside our solar system exhibit inflated radii or excess heat. Helium rain and internal heating mechanisms offer possible explanations. Saturn serves as a local laboratory for testing such models. Its well-studied properties provide ground truth for interpreting distant worlds. Saturn's thermal history also affects its ring system. The rings cast shadows that alter localized heating in the upper atmosphere. Conversely, the planet's internal warmth contributes to ring-moon interactions via radiation and magnetic fields. These feedbacks demonstrate how internal and external systems are interconnected. Heat is not confined, it shapes the entire Saturnian environment. The heat output is measurable via Saturn's effective temperature, about 95 K, versus an equilibrium value of about 75 K. This 20 K difference reflects the internal contribution. Over time, Saturn will cool as helium rain diminishes and residual energy escapes.
However, this process takes billions of years due to the planet's size and insulation. Saturn remains thermally active today. Future missions could refine our understanding with better interior probes or gravitational mapping. Helium rain, core structure, and thermal convection are still active research areas. In situ measurements could confirm models and resolve current uncertainties. These investigations will deepen insights into gas giant evolution and internal dynamics. Saturn remains a key target in planetary science. In summary, Saturn's heat is not just a remnant of its past, it's a continuing product of deep internal processes. Helium rain and slow contraction sustain the planet's energy output. This excess heat powers atmospheric motion, influences magnetic fields, and reveals the planet's interior structure. Saturn's hot internal clock continues to tick beneath its cloudy surface.
It would float. Saturn's low density. Saturn is the least dense planet in the solar system, with an average density of about 0.687 grams per cubic centimeter. This is lower than the density of water, which is 1 gram per centimeter cubed. The implication is striking. If there were a large enough ocean, Saturn would theoretically float. While this is purely hypothetical, it highlights the planet's composition. Saturn's bulk is made mostly of hydrogen and helium, the lightest elements. The planet's mass is immense, over 95 times that of Earth, but its volume is even larger. Its equatorial diameter exceeds 120,000 kilometers, making it the second largest planet after Jupiter. This massive volume dilutes its mass into a low average density. The result is a gas giant that is huge but relatively lightweight for its size. Its low density contrasts sharply with rocky planets like Earth or Mars. The bulk composition of Saturn explains this low density. It consists predominantly of molecular hydrogen, followed by helium and trace amounts of heavier elements. Hydrogen has a very low mass per unit volume, especially in its gaseous form. Deeper in Saturn's atmosphere, hydrogen transitions into a liquid state under immense pressure. But even in liquid form, hydrogen contributes to the planet's buoyancy. Helium adds some density, but remains lighter than most elements found in terrestrial planets. Saturn's atmosphere contains less helium than expected, likely due to helium rain settling toward the interior. This helium depletion in the upper layers further reduces average density. Saturn's interior may contain a denser core, but it accounts for only a small fraction of total volume. The outer envelope dominates the density calculation. Saturn's density varies with depth. The outermost layers are the least dense, composed of molecular hydrogen. As you move inward, pressure increases dramatically, compressing hydrogen into metallic form. This metallic hydrogen is denser, but still not comparable to rock or iron. The average density reflects the entire volume, from core to upper atmosphere. It's the mean, not peak density that allows the floating analogy. The floating concept assumes an enormous ocean, far beyond anything on Earth. The ocean would need to be large enough to submerge a planet over 120,000 kilometers in diameter. No such body of water exists, of course, but the thought experiment illustrates Saturn's physical makeup. It's an accessible way to communicate the planet's structure. This analogy is commonly used in science education. Cassini and Voyager missions provided precise measurements of Saturn's mass and volume. These parameters allowed accurate calculations of average density. They also revealed how Saturn's density compares to other gas giants. Jupiter, though larger and more massive, has a density of 1.33 grams per cubic centimeter, nearly twice that of Saturn. This difference is due to Jupiter's higher core mass and greater internal compression. The low density affects Saturn's gravitational field and orbital dynamics. Its gravitational pull is weaker at the surface compared to Jupiter despite its large size. This influences satellite motion and ring dynamics.
The planet's mass distribution, informed by density, plays a role in tidal interactions with its moons. These interactions affect moon orbits and internal heating, especially for moons like Enceladus. Saturn's low density also contributes to its extreme obliqueness. The planet bulges at the equator due to rapid rotation, completing one rotation every 10.7 hours. This fast spin, combined with low density, causes the equator to be significantly wider than the poles. The difference between equatorial and polar diameters is more than 10,000 kilometers. The shape is a visible effect of the internal mass distribution. The planet's lightness is not uniform throughout its structure. The core is hypothesized to contain heavier materials, possibly rock, ice, and metallic compounds. However, the core is likely diffuse and mixed with lighter elements. This diluted core model is supported by gravitational data from Cassini. The presence of a non-solid core also aligns with Saturn's thermal and magnetic characteristics. The low density influences how Saturn interacts with solar radiation and interplanetary particles. Its thick atmosphere extends far above the denser core region. This expansive envelope scatters and absorbs sunlight differently than solid planets. It also means that incoming particles from solar wind or cosmic rays encounter a vast, diffuse medium. These factors affect auroras and magnetospheric behavior. In terms of planetary evolution, Saturn's low density reflects its formation environment. It likely accreted from a protoplanetary disk rich in light gases. Its rapid growth allowed it to capture vast amounts of hydrogen and helium before solar winds cleared the disk. The result is a gas giant with a massive yet fluffy composition. This structure has remained stable over billions of years. Saturn's density also has implications for exoplanet studies. Many discovered gas giants around other stars, called hot Jupiters, show similarly low densities. These exoplanets are often inflated due to intense stellar radiation. Studying Saturn helps calibrate models for interpreting such systems. It serves as a local benchmark for planetary structure and gas retention. Despite its low density, Saturn's internal pressure is enormous. The weight of its massive atmosphere compresses materials to extreme conditions. Hydrogen at the center exists in metallic form, conducting electricity and generating magnetic fields. Even though it could float in water, Saturn's interior is far from gentle. It's a place of crushing pressure and high temperature. In summary, Saturn's density, less than water, reflects its gaseous nature and formation history. This quality gives rise to the whimsical notion that it would float in a giant ocean. But beneath this simple analogy lies a complex planetary structure, shaped by physics and time. Saturn remains a lightweight giant, both elegant and scientifically revealing.
Oblate planet, Saturn's flattened shape. Saturn is the most oblate planet in the solar system. Its equatorial diameter is significantly larger than its polar diameter. This shape results from its rapid rotation combined with low density. The planet completes one rotation roughly every 10.7 hours, creating strong centrifugal forces. These forces push outward at the equator, causing it to bulge. As a result, Saturn is distinctly flattened at the poles. Measurements show that Saturn's equatorial diameter is about 120,536 kilometers, while its polar diameter is approximately 108,728 kilometers. That's a difference of nearly 11,800 kilometers, visible even in telescopic images. The degree of flattening, or oblateness, is approximately 0.09796. This makes Saturn more visibly oblate than Jupiter, despite being less massive. The shape is a clear signature of dynamic rotation. The rapid rotation stretches the outer atmosphere outward, creating an equatorial bulge. This affects not only the planet's visible shape, but also its internal pressure distribution. The centrifugal force counteracts gravity at the equator, reducing the effective weight of atmospheric layers.
This leads to a thicker, more extended atmosphere at low latitudes. The effect diminishes toward the poles, where centrifugal influence is minimal. Saturn's low density amplifies the effect of oblateness. The planet is composed primarily of hydrogen and helium, which are easily deformed under force. A more rigid planet, like Earth, can resist such deformation, but Saturn's gas envelope responds fluidly to rotational stress. This allows the equator to expand significantly without structural resistance. The result is a pronounced planetary bulge. Cassini observations confirmed the precise shape of Saturn by analyzing its gravity field and atmospheric profile. These data helped refine models of interior structure and rotation rate. They also revealed latitudinal variations in atmospheric thickness. The oblate shape is not merely superficial, it reflects deeper dynamical behavior. Saturn's shape tells us how mass is distributed within. The oblate geometry influences Saturn's gravitational field, especially in its J2 term, a measure of equatorial bulge. These variations in gravity affect satellite orbits and ring dynamics. Moons and particles near the equator experience slightly different forces than those near the poles. This leads to subtle shifts in orbital paths over time. Accurate models must account for Saturn's true shape. Oblateness also affects Saturn's atmospheric circulation. The equatorial region receives different energy and experiences different dynamics than the poles. Zonal wind speeds and cloud bands are shaped in part by the planet's geometry. Cassini measured winds up to 1,800 kilometers per hour, especially strong near the equator. These wind patterns are modulated by rotational and gravitational forces tied to oblateness. The visual appearance of Saturn's shape changes with viewing angle and ring tilt. From certain angles, the flattening is evident in silhouette. Amateur astronomers can detect this distortion with modest telescopes. It's one of the few planetary features observable from Earth without space missions. The planet's shape reinforces its identity as a gas giant. Saturn's oblate shape also has implications for its internal dynamics. The core must be centered despite the outward push at the equator. This creates complex patterns of internal circulation and pressure balancing. Models of Saturn's interior must accommodate these non-spherical conditions. The core's gravity and the envelope's pressure interact in 3 dimensions. Oblateness plays a role in ring behavior. Saturn's rings orbit in the equatorial plane, aligned with the bulging equator. This alignment ensures gravitational stability and minimizes perturbations. The ring's vertical thickness is only tens of meters, but their radial position matches the equator exactly. The planet's shape helps maintain this delicate arrangement. Saturn's magnetic field also reflects its rotational symmetry. Unlike Earth or Jupiter, Saturn's magnetic field is closely aligned with its rotation axis. The near-perfect alignment may be connected to its symmetric internal structure. The planet's shape and spin contribute to this configuration. Oblateness thus links surface shape with electromagnetic properties. Over time, changes in Saturn's rotation could alter its oblateness. However, current data suggest its spin rate is stable. The planet's moment of inertia and angular momentum resist rapid change. This stability supports long-term equilibrium in ring and moon systems. Saturn's flattening has remained consistent over astronomical timescales. Comparing Saturn with other planets illustrates the unique degree of its shape. Earth is slightly oblate, with only a 21-kilometer difference between the equator and poles. Jupiter is more oblate than Earth, but less than Saturn. Uranus and Neptune rotate more slowly and show less flattening. Saturn stands out as a case study in rotational deformation. Understanding oblateness helps in studying exoplanets as well. Observations of distant gas giants may reveal similar bulges via transit photometry or spectral line broadening. Saturn serves as a benchmark for interpreting these indirect signals. Its shape provides a foundation for understanding how rotation sculpts large planets. In summary, Saturn's oblate shape is more than cosmetic. It reflects deep physical processes.
Rapid rotation, low density, and fluid composition all contribute to its equatorial bulge. This shape affects gravity, atmosphere, rings, and internal dynamics. Saturn's visible flattening is a gateway to comprehending its structure and behavior as a gas giant.